Hello, everyone, and thank you for joining us today. Welcome to the second annual UKSEDS Student Space Symposium. I'm Josh, and I'll be your host for today. We have a great lineup today, and as implied by the name of the event, all of our talks will be given by students and recent graduates who will be speaking on topics including artificial intelligence for Earth observation, reusable rocketry, Martian exploration robots, astrophysics, levitation in hypergravity, and plenty more. It was really tough competition for each of these speakers to be selected for the symposium today, but we have selected only the very best papers for you to enjoy. Each speaker has 10 minutes to talk to you about the papers they've written, which will be made available on the UKSEDS website after the event, and between 2 to 3 minutes afterwards to answer some of your questions. We'll take a short break between each speaker so that you have a chance to stretch your legs or grab a drink. We also have scheduled 2 slightly longer 10-minute breaks within the day and an hour for lunch to make sure you're not sat in front of a screen for too long if you do want to catch all of the talks. So if you're watching through the Nebula platform, you'll be able to access information about each of our speakers and sponsors using the information tabs on the top right corner of your screen, and send in questions to each of our speakers using the Q&A function, all while viewing the stream. We encourage you to use the Q&A function as much as possible. However, due to our tight schedule, we may not be able to get all of your questions answered live. If you only want to watch the stream and don't care about the function on the sidebar, you can hit the big watch button so that it takes up more of the page. Just a heads up, we recommend viewing the platform in full screen mode on Chrome wherever possible to get the best viewing experience. Today we're going to be live tweeting the symposium, and we're going to be posting on our Instagram page about all the speakers that are coming up. So whether you are an avid tweeter or Instagrammer, make sure to engage with us by tagging UKSEDS and using our hashtag Student Space Symposium. We'd like to say a huge thank you to the British Interplanetary Society, who are an organising partner of this event and who will be publishing a selected few papers from the symposium in a special UKSEDS edition of their journal, the Journal of the British Interplanetary Society. We'd also like to thank our fantastic sponsors, Astro Agency and Bryce Tech, who without we wouldn't be able to run events like this. As a charity, we rely almost solely on sponsorship from companies and organisations within the sector and really appreciate that they're able to support us. They're doing some very exciting things in the sector, which you'll be able to hear about them throughout the day during their sponsor talks or at the Careers Fair, which you can join again through the sidebar function on Nebula by clicking on one of the virtual stands and joining the queue. Before we kick off with the talks today, I'd like to tell you a little bit about some other upcoming UKSEDS events. For those of you who aren't familiar with UKSEDS, we're the UK's National Student Space Society. We're entirely run by students and recent graduate volunteers. We aim to provide opportunities like the Student Space Symposium to upskill and educate primarily university students, helping them to break into careers in the space sector. So the first thing I'd like to tell you about is the Terra Nova Hackathon, which is returning for its second year. The event's going to be taking place virtually over next weekend from October 15th to 17th, with teams of up to 6 students competing in one of 3 challenges set by space industry professionals from Spaceport Cornwall, the European Space Agency, and SSPI. The challenges will focus on areas including space mission design, Earth observation data analysis, and space education and outreach. The theme this year is sustainability, and as the UK space industry undergoes rapid growth, it's important to consider how the sector can contribute to the fight against the climate crisis and remain sustainable itself. The winning submissions for each challenge will be showcased by UKSEDS at COP26, the UN's 2021 Global Climate Summit, to demonstrate both the contribution of the UK to the UN Sustainable Development Goals and the innovation of its students and young professionals. Winning teams will also have the chance to present at SSPI's annual awards in December and will receive prizes ranging from company merch and gift cards to VIP launch invites. The hackathon will provide an interdisciplinary experience, and students of all levels of technical experience are encouraged to join. You can find out more and sign up for free either as an individual or as a team on the UKSEDS website. Another thing I'd like to tell you about is our competitions. We're soon going to be launching our core competitions, which take place annually. We've got the Satellite Design Competition, the National Rocketry Championship, and the Olympus Rover Trials. If you're keen to take part, make sure you sign up. You must enter as part of an affiliated university branch, which you can do quickly and for free on the UKSEDS website. There's more information available on the UKSEDS website if you'd like to learn more. but keep an eye out because we'll be launching these shortly. We've also got some new competitions coming out this year. So in addition to those core competitions that I talked about, we're going to be launching these 3 new ones, which are based on CubeSats, larger rocketry, and in-orbit manufacturing. Excuse me. Another initiative run by UKSEDS is Space Projects, which is organised by UKSEDS in collaboration with the Space Universities Network and is supported by the Satellite Applications Catapult, the UK Space Agency, the European Space Agency, and the South Coast Centre of Excellence in Satellite Applications. In the final or penultimate year of their degree, students have to complete a lengthy individual project, and space-related topics are often unavailable. Space Projects provides the framework for students to do their project remotely with a space organisation and advertise projects proposed by space organisations to students nationwide on a rolling basis. The space sector is one of the fastest growing sectors in the UK. Employers, however, often highlight a lack of skilled graduates and students, a lack of opportunities to get this experience. The scheme has been created to give students this crucial experience and has been designed upon feedback from several academics, space industry professionals, and students. So make sure to check out the website if you're interested. If you want to keep in touch with UKSEDS, you can sign up to be a member at our website, ukseds.org/join. You can also subscribe to our newsletter, Ecliptic, to stay up to date on space projects, events, and opportunities. You can also join or set up a local branch at your university. If you want to join us as a volunteer, keep an eye on spacecareers.uk, our careers website, which will advertise any opportunities we have available on the team. Alternatively, you can register your interest by scanning this QR code. So I've now been speaking for quite a little bit. So without further ado, I'd like to welcome our first speaker onto the stream, who will be giving the first presentation of the day, which is Space Health and Disaster Risk Reduction by Miles Harris. Miles is a PhD student at the UCL Institute for Risk and Disaster Reduction. Miles is researching prolonged field care, which is pre-hospital health in remote environments with limited accessibility and resources, in collaboration with Remote Area Risk International and the Ministry of Defence, Royal Centre for Defence Medicine. Miles is a coordinator of UCL Space Health Risk Research Group and is leading the first UK pilot analogue research mission. Apologies. So Miles will be joining us shortly and will give this presentation. the live call. So I think we will go to our next speaker, and we'll bring Mars's talk to you in a little bit. I will again go back to him and reintroduce him properly so we don't miss out on his fantastic research. Instead, for our first talk, we will have an investigation of ESA's RAM EP intake via direct simulation Monte Carlo by Claudio Rapisada. So Claudio has recently graduated in aerospace engineering from the University of Manchester, where he actively engaged with several aerospace projects and societies. He was a mission analysis and GCS engineer in the Manchester CubeSat Research Group, student representative at the Manchester branch of the Royal Aeronautical Society, descent control engineer in the Manchester CANSAT Group, industrial liaison at the Aerospace Society, and member of MANSEDS. For his research thesis, Claudio undertook a design and optimization investigation on passive intakes of atmosphere-breathing electric propulsion systems. This involved the implementation of analytical models as well as the use of direct simulation Monte Carlo. Claudio is now studying an MSc in space engineering at the Technical University of Delft and is an active member of Delft Aerospace Rocket Engineering. Hello, Claudio. It's great to have you here. Thank you so much for joining us today.
Good morning. Thank you very much for having me. Yeah, should I try and share my screen now?
Yeah, you're welcome to take it away whenever you're ready.
Great. Okay. Should be able to see it now.
Yep. There we go.
Amazing. Okay. Well, thank you very much. Good morning, everyone. Thank you very much for having me. It's a huge pleasure to be here, be able to present my investigation of ESA's RAM intake via direct simulation Monte Carlo. So I'm just going to give a very brief overview of the presentation. I'm going to start off by introducing the very low Earth orbit environment, along with its key benefits and challenges. And then I will talk about the atmospheric breathing electric propulsion, or ABEP concept, and the solution that it offers. We'll focus on the RAMEP model, which is the case study of the presentation. And I'm also going to talk a little bit about the rarefied gas dynamics, just to give a little bit of a deeper understanding of how the environment plays a role in the intake. And I will then talk and introduce the direct simulation Monte Carlo method, or DSMC, and how the model is implemented in the simulation and the results obtained. So the blue environment is that region of the atmosphere which is defined as being between 100 and 450 kilometers, where the lower boundary is the Kármán line, the threshold to space, and 450 kilometers is the point or the altitude beyond which you can neglect the effect of atmospheric drag on a spacecraft. And the reason why spacecrafts operate in blue is that there's a number of benefits associated to that. For instance, in terms of payload benefits, optical payload improve the spatial resolution, or if you have an SER payload, you're improving the signal return, you're also improving the geospatial position, angular field of regard, and a number of other parameters associated to the orbit. And that's purely because you're flying closer to the target. You're also improving the launching capabilities because you're flying to a lower altitude, meaning that you can either reduce the launch costs, or for the same launch cost, you can increase the payload mass. And also there's a number of benefits associated to the environment because it's relatively benign in terms of radiation. You're reducing the risk of collision and complying with the 25-year deorbit requirements. And that's because atmospheric drag plays a very important role in VLEO. And drawing from this very last conclusion, we can see that we know that drag is proportional to density. We can see the plots for atmospheric density over a range of altitudes in VLEO. And we observe that the density is actually decreasing exponentially with altitude. And that's why drag is so remarkable, so important in VLEO. It's very high, and that limits the mission lifetime of a satellite. So typical space architectures would employ a propulsion system to compensate for this high amount of atmospheric drag experienced. But conventional propulsion systems, like electric propulsion, usually employ onboard propellant. And the amount of onboard propellant required is actually going to limit mission lifetime. So once the propellant on board the spacecraft has been depleted, the propulsion system is not going to be capable of compensating for drag anymore. And there's also more problems associated to onboard propellant, because that's going to increase the mass, it's going to increase the volume and potentially the surface area due to the tank of the propulsion of the propellant, for instance. So a further trade-off is then required. Atmospheric breathing electric propulsion, or ABEP, offers a flexible alternative. And this is because it turns the problem into the solution to the problem. And this is because it's employing the atmospheric particles, which are generating drag in the first place, as a propellant to the propulsion system. So looking at the schematic on the right, we can see that there's an intake facing towards the direction of flight, and that's collecting, scooping as many particles as possible, and then feeding them to the core of the satellite, where you find the second component of the propulsion system, which is the electric thruster. The second component is accelerating the particles, ejecting them at the back of the satellite, and creating an exchange of momentum, which translates into a positive thrust vector in the direction of flight. So we're going to be focusing on the intake, the passive aerodynamic intake at the front of the satellite, which requires two key performance parameters: the intake collection efficiency, which is just defined as the quantity of particles that reach the thruster out of the incoming flow of particles, and the compression ratio, which is just the ratio of the chamber density to the free stream density. Now, the case study of this research is the ramp model. This has been defined or devised by the European Space Agency study for a range of 180 to 250 kilometers. It's a cylindrical collector with a surface area, frontal surface area of 0.6 meters squared, and length of 1 meter. It's collecting as many particles as possible and feeding them to the gridded ion engine at the back. And you can also notice, quite interesting, the gridded structure at the front of the intake. And the function of this structure is to reduce the backflow of the particles. So once the flow enters the intake, it can't exit as easily. Now, in order to analyze and understand what's happening inside the intake, we need to very briefly introduce the concept of rarefied gas dynamics. So the Nutzer number has been plotted over a range of altitudes on the right-hand side for the RAMF intake. And the Nutzer number is just a quantity that characterizes the degree of rarefaction of a gas. So when this number is much greater than 10, the flow regime is considered as being free molecular flow, or FMF in short. And we can see that this happens above 124 kilometers in the case of RAMF. And in free molecular flow, we can't, the flow is not considered a continuum anymore, but we need to consider the individual collisions of the flow particles, so one-to-one with the spacecraft. And that means that we cannot use the classical mechanics equations anymore. And this is why we use the direct simulation Monte Carlo, or DSMC method. This is a stochastic simulation in which a representative number of atmospheric particles is computed within the computational domain just generated, and the individual collisions are recorded and measured over time. The solver uses DSMC Foam Plus within the OpenFOAM toolbox, and the CAD file has been generated according to the dimensions provided by the ESA study. It's been imported into the computational domain, and different boundary conditions have been assigned. And the methodology has been verified by comparing the pressure plot in the bottom left of DSMC Foam Plus with SMILE. SMILE is the DSMC simulation used by the ESA study. And we can see there's an agreement in the pressure flow behavior, as a constant pressure of 1 millipascal has been observed in the chamber of the intake, and peaks of 8 millipascals have been observed near the grid. What's more interesting is that the two performance parameters have been computed and plotted over a range of altitudes, and we can see an average of about 22% for the intake collection efficiency and compression ratio oscillating between 21 and 23. But what's actually interesting to observe here is that both parameters are decreasing almost linearly with altitude. So it might be desirable to operate the spacecraft at lower altitudes, but then you can experience more drag. So a trade-off has to be carried out. Taking a reference of 200 kilometers, the performance parameters have also been plotted for a range of incidence angles. This is to account for orbital perturbations or orbital maneuvers. And we can see that beyond 5 or 10 degrees, the performance actually drops. So the propulsion system is degraded quite significantly, and it probably means that these concepts cannot be used under these conditions. And finally, the thrust-to-drag ratio has been plotted. The thrust-to-drag ratio is a very important quantity because it defines the capability of the propulsion system to compensate for drag. So when this ratio is equal to unity to 1, drag is completely compensated for by the propulsion system. And when you have an excess, so when the ratio is greater than 1, the propulsion system can also account for orbital maneuvers, for instance. And thrust has been computed analytically, whereas drag has been computed numerically here. And we can see that when you increase the specific impulse of the thruster, you're increasing the thrust-to-drag ratio as expected. But what's also more important is that the ratio is greater than 1 at all altitudes considered, which means that the concept actually is feasible for all altitudes. So the main findings of this research, just to conclude, are that the methodology has been verified against the SMILE simulation. The performance parameters have been evaluated for the RAMET concept for different flow conditions. And most importantly, full drag compensation is achieved at all altitudes, meaning that the RAMET model is a feasible concept. And these are the references I've used. And with that, I come to a conclusion. Thank you very much for listening. Feel free to contact me at the email or any questions that you might have now. I'd be more than happy to take them.
Thank you so much, Claudio. That was a fantastic talk. Very enjoyable. And I'm sure our audience absolutely loved it. We have, in fact, got a few questions through, and we have some time to ask them. So I'll get right into it. The first one is, have you considered the relative weight and drag of solar arrays to provide sufficient power for the heating element?
I haven't considered that in this study, but there's several studies that have accounted for that. If I go back to the amount of power that's required by the thruster, you can see that if you want to increase the performance of the propulsion system, you're going to have to increase the power generated. So that's going to give you a rough estimate of the amount of power required. But that's, of course, going to depend on the actual type of solar panels chosen for the concept.
Wonderful. The next question we have is, did you consider the use of an aerospike or other alternate nozzle shapes?
Yeah, well, that's actually very interesting because there's a number of comparisons between a ABEP concept and a scramjet or an aerospike. The issue is that we are operating in a free molecular flow, so the actual flow behavior is very different. When it comes down to comparing the two, unfortunately, the aerospike would not be a feasible concept applied to an ABEP design, and that's because the collisions are actually diffuse. So when you're when the flow particles interact with the surface of the satellite, the particles are entirely absorbed by the surface and then re-emitted at the same temperature of the surface of the satellite, meaning that you have a complete accommodation coefficient. So the direction of scatter is actually random, and that's why an aerospike would not actually be a feasible concept applied to ABEP.
Brilliant, thank you. We have one more question, which is, would any adjustment need to be made to the propellant to facilitate this alternate heating?
Well, you could make the system active in terms of improving potentially the collection as opposed to the heating, but that's going to require more power. So the advantage of ABEP is that it's a passive. Well, in this case, the intake is a passive system, so it doesn't require any external heating power. But the idea of increasing the heat on the surface of the wall is that you might increase the intake performance efficiency, and that's because, as I just mentioned, the thermal accumulation coefficient tends to be towards 1. But if you found a way to change the temperature of the walls, so by active heating, for instance, you could regulate the thermal accumulation coefficient, and therefore you could make the collisions quasi-specular. and that's going to, of course, drive the collection efficiency up. So yes, a number of studies have been considering that, and it can certainly be implemented, but that's going to require further power.
Brilliant. Thank you so much. That's all the questions we had. But if anyone has any further questions, feel free to send them through later. We'll make sure they get to Claudio. But yeah, thank you so much for your paper and for your wonderful presentation. Yeah, for coming along.
Thank you very much. Great experience. Thank you for having me.
Wonderful. So we're now going to get back on schedule with Miles. So we'll get straight into his talk so that we aren't running too behind. So once again, I will introduce Miles, just so you remember what his research is on. So Miles's research is on space health and disaster risk reduction. And so Miles is a PhD student at the UCL Institute for Risk and Disaster Reduction. He's researching prolonged field care, which is pre-hospital health in remote environments with limited accessibility and resources, in collaboration with Remote Area Risk International and the Ministry of Defence, Royal Centre for Defence Medicine. Miles is a coordinator of UCL Space Health Risks Research Group and is leading the first UK pilot analog research mission. Hello, welcome back. Sorry for that delay once again. We encountered some technical issues getting Miles here for his talk, but thankfully Miles is with us now, so we'll be able to begin his presentation on space health and disaster risk reduction. So, Miles, yes, lovely to have you. Thank you so much for submitting your paper and for joining us today to give a presentation. So whenever you're ready, feel free to go ahead.
Brilliant. Thank you very much, Josh. And thank you to Zari and Aaron for their technical support. There was a few issues, and we were saying that Murphy's Law has striked again. But nevertheless, we made it in. Thank you very much for everyone to tuning in. My name is Miles, and the title of my presentation is Space Health and Disaster Risk Reduction. My background is that I'm a nurse, and my master's was in education. And I'm currently doing a PhD in risk and disaster reduction at University College London. For my PhD, I'm looking at something called prolonged field care, which is a military healthcare term that describes the provision of healthcare in very remote environments around the world, in environments that have limited accessibility and minimal resources. My other role at University College London is I'm a coordinator of a research group, and the research group is Space Health Risks Research Group. And the research group is a multidisciplinary community of researchers and practitioners that have come together to investigate the risks to health in space and to learn from that risk and the mitigation of those risks and apply it to remote environments on Earth to benefit life and good health and well-being. There are two projects in the research group that have informed the paper that I've written for this symposium and also for this presentation as well. I'm going to be speaking for just under 10 minutes, and I'd be more than happy to answer any questions towards the end as well. So the first project that I'd like to refer to is a symposium that the research group had just over a month ago, and that was on space health and disaster risk reduction. This symposium was funded by UCL Grand Challenges, and we had 240 people book tickets, with people tuning in throughout the day from Australasia through to Asia, Europe, and North America. The symposium was a theoretical exploration of how healthcare could be provided during the exploration of another planetary body, and how that sort of practice could be applied to remote healthcare systems on Earth. What we focused on during the symposium was interdisciplinary healthcare. And what we mean by that is, as healthcare practitioners, we know our scope of practice very well. So, for example, I know nursing practice very well. And I know what other members of a multidisciplinary team do, such as doctors and allied health professionals. But on planet Earth and in urban environments, if I need their expertise, I'd either reach out and speak to them in a hospital environment or pick up the phone and use telemedicine. But in remote environments on Earth and in space, that's very tricky to do due to a number of challenges, and technology is often not as reliable as we would like it to be. And perhaps this morning is a good example of that. So interdisciplinary healthcare means the provision of healthcare, but wearing all of those hats at the same time in order to meet the healthcare needs of the patients that we're looking after. And we examined interdisciplinary healthcare from 5 perspectives of health. And those 5 perspectives were space health and space medicine. We looked at global health and public health. We looked at planetary healthcare systems, including medical practice, nursing practice, and allied health professional practice. We looked at anthropology, and we also looked at the disaster sciences. What I've included in the paper is reporting on the risks to health that were discussed during the symposium, and then also the challenges of interdisciplinary healthcare. There were many risks that were discussed and highlighted and debated throughout the symposium, and they were grouped into 3 categories. They were physiological risks to health, psychosocial health, risks to health, and then also environmental risks to health. And for an interdisciplinary healthcare practitioner, they would need to have awareness and be able to mitigate all of those risks in order to protect and promote the good health and well-being of astronauts during the exploration of another planetary body. which also applies to remote environments on Earth. Some of the risks that we discussed were bespoke and only would be applied to a space environment. So, for example, the exposure to high levels of radiation we don't experience on Earth as much as we would in space, such as on the Moon or on Mars. But a lot of the risks that are a risk to health in space do apply to remote environments, such as long exposure to periods of isolation. The recent COVID-19 pandemic is a really good example of how long periods of isolation can negatively affect both physical and psychosocial health as well. Some of the challenges to interdisciplinary healthcare, however, there's actually minimal literature that looks at how these risks to health can be applied to interdisciplinary healthcare, and also being applied to space environments and remote environments on Earth. And the second challenge that we discussed was fostering a learning culture, because that's really the catalyst of how interdisciplinary healthcare can be achieved, is that individual needs to be able to learn from different people, from different professional backgrounds. And that really is a key to unlocking interdisciplinary healthcare. So much more research is needed in this context of interdisciplinary healthcare on another planetary body. And this leads to our second major project, which is an analog space mission. So we're doing a human analog space research mission. There's been some analogs in the UK that focus on robotics, but there's never been a human analog mission before. So we're going to pilot the first one, which is going to take place in spring next year, 2022. The location of the analog is going to be a remote and uninhabited island in Scotland. And what we'll be simulating is the exploration of another planetary body. We're keeping that exact location quite secret because we don't want analog astronauts to be able to explore the island on Google Earth, for example, because we're simulating the exploration of another planetary body where nobody's been there before. One of the things that draws a connection between these two studies is during the symposium, we asked the participants to share ideas about realistic healthcare scenarios that could happen during the exploration of another planetary body. We're going to take a sample of 3 of those scenarios and enact them as case studies during the analog mission. The analog astronauts will need to be able to stabilize patients and provide continuity of care for 8 hours per case study. And what we're going to do is to evaluate the consensus of interdisciplinary healthcare that will be established through the data collected through the symposium and evaluate that through those case studies. There's a variety of other studies that are going on during the symposium, such as an astropharmacy study. We're doing an ethnographic study that contributes to medical anthropology, and also looking at some AI and technology studies as well. So there's a multidisciplinary team of people behind the scenes that are working on this analog mission. As I say, we're going to do that analog mission next spring. One of the things that we're particularly focused on in the planning of this analog mission is distinguishing between the in-simulation risks to health and the in-reality risks to health. As healthcare practitioners and as researchers, we have a duty of care to the research participants and research staff. So we have a team of people that will be purely focusing on the provision of healthcare in reality, as if we're going to a remote and uninhabited island on Scotland. So we have a doctor and a team of mountain leaders that are qualified to guide people in UK mountainous terrain. The analog astronauts will be a variety of different healthcare practitioners, and we're purposely selecting those to be able to get a representation of a multidisciplinary team, and that will enable us to evaluate that interdisciplinary healthcare consensus that will come out of the symposium. With just under a minute and a half to go, thank you very much for listening to my presentation and reading the paper. If you have any questions about the research projects that we have or the research group, then please feel free to email us with the email address on the screen, or you can contact me on Twitter. So thank you very much for listening, and I'm more than happy to answer any questions.
Thank you so much, Mars. That was another fantastic presentation. And it was worth the wait and overcoming the issues that we had to have it presented to our attendees. We do, in fact, have a number of questions. So the first of these is, if you were to assess the relative impact of different issues, which would be the most important health and disaster problems overall that you'd say need to be solved?
That's a really good question. Thank you to whoever asked that. And my answer to that would be the biggest risk would not be joining the connections between all of the holistic risks to that individual, to patients in space and in remote environments on Earth. If we purely focus on providing health from a biomedical perspective, and what I mean by that is purely focusing on the physiological health of people, psychosocial health is potentially neglected, which no healthcare practitioner wants to do. So without joining the connection between all of those risks, we're not able to provide holistic care to the patient. There's lots of literature that looks at the risks to health in space. NASA's doing some really good work, as well as UK research institutions as well. So if you'd like some papers on that, then get in touch and I'll be able to share them with you.
Thank you. The next question is, how did you navigate engaging with engineering and scientific professionals and using that experience for healthcare?
So this project has actually attracted quite a lot of interest, which is a really pleasant surprise, and I'm thrilled by that. The only way that we've advertised the analog mission so far is through our webpage. And it's through the webpage that people have contacted us and said, we really like your idea. We have this research study that we would like to do during your analog mission. And lots of those studies align with the research group aim. So we've gone to the steering group and asked their opinions on what those studies would be, whether they would be a contribution to. So we're still planning and still organising the analog mission. So again, if anybody has any interests or thoughts in the analog mission, then please feel free to get in touch.
Wonderful, thank you. So we have time for one more just before we go ahead to our next speaker, which is, how do you decide when risk is simply too great in a space setting when there are so many unknowns and unavoidable risks?
Another great question, and actually that applies to remote environments on Earth as well, particularly exploring high-risk environments such as high-altitude mountaineering. It's a very complex risk assessment, and specific risk assessments before deployment to space or remote environments can only get you so far. So it's about looking at what risks exist and that we know about and mitigating them before we go, such as pre-deployment training and resources. But it's also an element of dynamic risk assessment on the ground, in the field, during a space exploration mission or in remote environments. And the answer to that is to have an experienced practitioner that's able to provide interdisciplinary healthcare and also is competent and confident enough to assess those risks on the ground in the field. So that's my answer to that question. Thank you.
Thank you. Another wonderful answer. Very insightful talk and very insightful answer to some great questions. So thank you very much, Miles, for coming along today. And I'm sure everyone's looking forward to reading your paper once it's up on our website.
Thank you very much. And thanks so much for being patient with me with the...
Your apologies for the difficulties. And again, apologies to the viewers.
No problem. Thanks very much, everyone.
Okay, so I'm aware that on our schedule, it says now that we're time for a break. But just to make sure that we stay relatively on track and finish on time, we're going to go ahead with our next speaker, Wojciech, in a couple minutes' time. I just want to say a quick apologies to the difficulties with the scheduling, and if you have come along for a specific talk at a certain time, or you were planning on attending a talk at a specific time and this no longer works with your schedule, we understand it can be quite difficult if you're coming to a certain talk and things get tossed up a little bit. However, the recording of the symposium will be available on our website and on YouTube after the event. So if you've missed something or you're going to miss something, there's still time to catch it. Yes, we'll be back in a few minutes with our next speaker, so hang tight and stay tuned. Hello and welcome back. We're now joined by our next speaker, Wojciech Stogowski, for his talk on potential oasis on Enceladus. So Wojciech has just finished his BSc degree in planetary science and astronomy with the Open University. He's originally from Poland and moved to the UK in 2005. Space and science are the areas of his passion and his keen interest. Hello, it's wonderful to have you. Thank you so much for joining us. Yeah, we're ready for your talk whenever you're ready to take it away. So go ahead.
Hi there, welcome everybody. Thank you for having me. It's a great privilege to present in my work and my paper. Hope everybody will enjoy my presentation, which, as Joshua said, is on Enceladus and the potential life on this tiny moon of Saturn. Hope everybody can see currently my paper.
We can't see your screen currently.
Okay, yep, I'm on it right now. Hope it's visible right now.
We can't see the screen, but alternately, I'd be happy to share the presentation and change slide whenever you ask, if that works.
That would be fantastic. Thank you very much for your help, Joshua.
Awesome. You're very welcome.
I'm ready to go wherever you are.
Sure. There we go. I believe that's now visible. So ready to go whenever. And if you'd like me to move to the next slide, just let me know.
Fantastic. Thank you, Joshua. Yes, so welcome everybody to my presentation on Enceladus. We are currently on the first slide, which presents us a little bit of a background about the Enceladus itself. It's one of the innermost and the sixth largest Saturn's moons. It's also one of the most interesting ones, although it has escaped our attention since its discovery in late 1700s. We basically thought about the Enceladus as being just, a cold and rigid snowball, but our knowledge and approach drastically changed when the first images and data from Cassini mission arrived back on Earth. And from those images and data, we could see there is a very varied geology happening on the surface of the Enceladus. We do have the northern hemisphere that is heavily cratered, which indicates it's pretty much very old terrain, not being resurfaced by any geology or any activity. And then we do have the southern hemisphere, which is relatively smooth and also covered in very mysterious and spectacularly looking fractures called tiger stripes. And this tells us that the southern hemisphere is much more younger terrain and is also geologically active. Hence, it doesn't have all those heavily cratered, marks on the surface. What else we find out from the Cassini Space mission? That this icy snowball is not really that rigid, and there is a global ocean present underneath this ice shell. That being discovered by the Cassini onboard ice-penetrating radar, but also we managed to find out plumes above the Enceladus surface, and that consists of water, ice, and many very interesting chemicals. So we could see clearly there is activity going on in the Enceladus interior. Now, the key questions are, where is this source of energy coming from? Why all the activities is focused on the southern hemisphere on the Enceladus? And what drives this geology? Which I'll try to answer in the following slides. And I'm ready for the next one, Joshua. Thank you. Now, on this slide, we can see the northern and the southern hemisphere and the arrows then pointing on the key features. On the top of the image, we can see cratered older northern hemisphere. And then on the bottom of the image, we can see much smoother and heavily fractured southern hemisphere surface, which is much younger and covered with tiger stripes fractures, which I will try to explain their origin in the following slides. And I'm ready for the next one, Joshua. Thank you. Okay, now a little bit of a science. This is data from the Cassini mission. And as a scientific method, Cassini images has been used to map the surface features and to compare them with the radar and infrared thermal emissions that also has been measured by the spacecraft. And using this approach, thermal anomalies has been discovered very close in location to a active sulky, also known as fractures. And that work has been done by Goll and his team in 2017. In another investigation, computer software models has been used by Rodden et al. And his team in 2020 to model the distribution of tidal stresses that are basically being exerted by the Saturn on the Enceladus surface that causes the tensions and the cracks. And the modeled distribution has been compared with the position of the real fractures. And there was a very, very good match in the data modeled by the computer simulations and the fractures being observed on the photographs. And we can see it in the results that we have thermal anomaly very close to those mentioned area thermal, tiger stripes fractures, which on the occasions became they became active and they eject plumes into the space. And we can see there is a thermal anomaly located very close to them with temperature increased by 32 to 60 degrees Kelvin, which is way too high to be of an external origin, suggesting that it has to be an internal heat source present in the Enceladus interior. And below we can see the simulations run by Rodden et al. That shows the orientations of tiger stripes fractures do coincide indeed with the modeled distribution and location of the tidal stresses that are exerted by the Saturnian gravity. And we can see on the figure on the bottom of the slide that both the simulations and the actual position of the tiger stripes fractures peaked at 135.5 degrees clockwise from the longitude 0 west. So we have a correlation between the observed and the modeled data, suggesting that indeed those fractures has been created by tidal stresses exerted by the Saturnian gravity. I hope this slide wasn't too difficult to explain and to take in. And I'll answer any questions after the presentation, and I'm ready for the next slide. Thank you. Now, on this slide, we have a proposed model of the Enceladus interior. We can clearly see on the top of the image the ice shell that covers the entire moon. But we can also see that there is a global ocean present underneath the ice shell, approximately on the depth of 65 kilometers. But also on the bottom of the ocean, we can see there is a interaction going on between Enceladus rocky core, which is being heated by tidal forces exerted by the Saturnian gravity, is basically being squashed and stretched. And as you would stretch and bend a metal rod or a spoon, it will heat up. So quite similar mechanisms happening in the Enceladus rocky core, which is also quite porous, absorbs the water, heats up that water, and potentially drives all the geology and the complex chemistry that is present in the Enceladus oceans. It's quite interesting because similar hydrothermal vents are also being found in the Earth's oceans, and they are oases for photosynthesis-independent life. We can see on the bottom of the slide the middle image of hydrothermal vents, so-called white smokers, which is actually a feature on ocean seabed. And I'll try to explain it in the next slide. Thank you. I'm ready for the next one. Yeah, this is the example of plumes that being ejected on Enceladus, and those plumes has been analyzed by Cassini instrumentation, and they find out it's been found out that they contain silica, salty water, ice, and quite a lot of other ingredients that are crucial for life. The plumes from Enceladus also feeds Saturn's E-ring, and they do precipitate on adjacent moons, increasing their reflectivity. So there is a material exchange mechanism between Enceladus and the Saturnian ring system, which is quite interesting on its own. And I'm ready for the next slide. Thank you. Now, in this slide, we see the examples of thermal vents. At the top of the slide, this is actual image taken on the Earth's ocean. But if we use our imagination as a possibility that similar thermal vents do exist on Enceladus, driven by the internal heat source, and on the bottom of the slides we do see in the figure 7, structures that are being grown in the laboratories on Earth, where water rich in iron ions has been injected into the salty waters that represent the ocean, either the Earth's ocean or the Enceladus ocean. And we can see that those chemicals combined together and injected one into the another under the pressure can create structures that are very strikingly similar to thermal vents that do exist in nature. And those features grown in the laboratory kind of prove the point and the possibility that similar structures could be detected on Enceladus oceans. Thank you. I'm ready for the next slide. We are approaching the end of my presentation. And to sum up the story I was trying to tell you, and hopefully I did successfully, the key point is that Enceladus is an active ocean on the edges of the solar system, and that the moon geology is driven by tidal forces exerted by the Saturn's powerful gravity independent of the solar radiation. And I think that has been proven to the certain degree of being sure about it, that we have totally independent from solar radiation source of energy on the edges of the solar system. It's far beyond sun habitable zone, and yet we do find this tiny world that is possibly habitable, and who knows, maybe the life originated in the oceans of Enceladus. To support this argument, we have the analysis of plumes ejected that contain complex chemistry and organic compounds not dissimilar to the Earth's oceans. And that chemistry and organic compounds is crucial to synthesizing complex amino acids, including RNA and DNA. We also confirm that those thermal vents structures could possibly be formed on the Enceladus in laboratory conditions. So we have kind of like a dual approach. We do have what already exists in the Earth's oceans and what could possibly be present in the Enceladus. And that strong analogy in the Earth's oceans, where around hydrothermal vents, totally independent from photosynthesis life could exist, it's a very exciting possibility that we might have photosynthesis independent life systems in our solar system. especially Enceladus. We also know there is a material exchange mechanism between Enceladus and the adjacent moons. Basically, all the material ejected by the Enceladus plumes feeds the Saturn's E ring and later on precipitates on adjacent moon surface. So in summary, Enceladus can be a habitable ocean world, and I think humanity should return with more sophisticated mission to try to confirm or deny our suspicion of possible life on Enceladus. Such a mission has been proposed by European Space Agency to be possibly launched in 2050. I would look forward to that kind of mission. I hope everyone enjoyed my presentation. Thank you very much indeed.
Thank you very much for another wonderful presentation. That was brilliant and very enjoyable. Unfortunately, just to get on time with our schedule, we're not going to have time for questions. But if anyone has any questions for Wojciech, I can send them through after the event, if that would be okay with you.
I'm quite happy to do that. I'm sorry if I went over the time.
No, it's okay. Sorry, we're obviously not quite on schedule just because of the technical difficulties.
Okay,
but yeah, thank you so much. So unfortunately, we're going to skip over our break and our sponsor talk to go ahead with our next speaker. However, if you do need to take a break, because we've been going for quite a while now, feel free to stretch your legs, grab a drink, maybe a bite to eat. Like I said before, this event is being recorded, so if you do want to take a break during one of the talks, you'll be able to catch up with it afterwards. So, our next speaker is Hari Prakash Dhanabalan, talking about development of analytic-inspired soft robots using low-voltage, fault-tolerant artificial muzzles for exploration of Mars. Hari is an MSc student in advanced robotics from Queen Mary University of London, where he focuses his research project on soft robotics. He has always been fascinated in space science and robotics since he was young. With the passion and interest he has towards these fields, he aims to someday develop biologically inspired soft robots for space exploration, particularly of the red planet. So, hi, Hari. Very, very good to have you here.
Thanks, Joshua. How are you?
Joining us. I'm good, thank you. I hope you're doing the same. We're ready for you to take it ahead whenever's ready for you.
All right, sure. So before I begin, just want to confirm that you guys can see the screen, yeah?
Yep, we can see that perfectly. Thank you very much.
Perfect. All right. So hi everyone, good afternoon. So my name is Hari Prakash. I've been introduced just now. So today I'll be sharing my research idea on the development of analytic-inspired soft robot using low-voltage, fault-tolerant artificial muscle for the exploration of Mars. Before I begin, what are soft robots actually? Soft robots are actually the forefront of robotics evolution. The term soft robot comes from the materials that they are being made from, such as silicon or fabric. Taking nature into consideration, soft robots aim to replicate and understand nature's competency and taking inspirations from animals and even from plants. There are various types of actuators for soft robots, such as electrically actuated, pneumatically, thermally, explosively, and shape memory alloy by using light. Soft robots are actually ideal for unstructured terrains, and because they possess about almost infinite degrees of freedom. And in comparison with rigid robots, soft robots are ideal for extreme mechanical deformation, meaning you can squeeze them, you can press them, you can twist them, and they can actually still work. So the most common application for soft robotics are minimal invasive surgery, exploration, search and rescue, and manufacturing. So here is a table of showing soft robots versus conventional robots. So the most prominent factor you got to take note of this is that the materials that soft robots use. Soft robots has reversible properties. It has low cost of manufacturing and weight, which would potentially lead to a lower cost of space exploration. It has infinite degree of freedom, and it is safe for human-machine interaction. So these are the example of soft robot. And the next slide, I'll just show you a short video on how this soft robot actually actuate in real life. So this is the pneumatically actuated soft robot. Sorry, electrically. This is pneumatically. Thermally or light. And explosively. Okay. So why do we need soft robots for planetary exploration? Number one, it's lightweight. Number two, manufacturing costs will be lowered and also lead to lower cost of space exploration. Since it has higher flexibility and adaptability, it is able to explore a planet thoroughly, even to tight crevices. So over here, I'll present my proposed fabrication for the Analyte robot. So the proposed design for this robot is actually based on an analytic creature such as an earthworm, because earthworm actually possess a very effective way of locomotion, usually locomotes in a peristatic manner, that is applicable to large variety of unstructured terrains, despite its simple structure. This design actually allows the robot to actually locomote in unstructured terrains and in secluded environments. So over here is my conceptual design of the Analyte-inspired soft robots. This soft robots consists of 6 DEAs. DEA stands for dielectric elastoma actuators, which is electrically actuated, that's embedded into the main actuator. Each DEA are independent of each other, and they are actuated independently. So when you actuate independently, it actually generates a square wave-like propulsion or locomotion. DEA actuation will actually result in axial elongation and circumferential descension. In the upcoming slides or further in this presentation, I'll show you how a DEA actually works. So before that, we'll move on to the condition on Mars, because conventional soft robots is not suitable for planetary exploration, because especially Mars, because Mars has low mean surface temperature and pressure, and due to the absence of global magnetic field, which gives it no protection from cosmic rays and solar flares, radiation in Mars is very high when it compares to Earth. Mars is prone to 3 types of radiation: GCR, radiation trapping belt, and SAP. And the main types or primary types of radiation includes alpha, heavy nuclei particle, electrons, and protons. So since soft robots are using elastomas, there are several properties are required to be assessed for space application. Number one is a DSC, which measures the temperature and heat flow of related material transition, such as the glass transition temperature, melting point, and etc. Number two is a TGA, measures mass loss due to decomposition. Number three, measures dielectric constant and loss of insulating conductivity. Number four is the DMA, measures the storage and loss modulus. And number five is the outgassing test. This measures the eventual mass loss in vacuum. So the proposed material for my robot would be a space-grade RTV silicon elastomer. RTV stands for room temperature vulcanized rubber. The reason I've chosen RTV is because it has excellent elasticity and electrical properties. It can be cooled down to minus 150 degrees C and heated up to 400 degrees C. Its relative total mass is less than 1% under outgassing condition in high vacuum. And also a mixture with butadiene rubber provides the robot with a greater mechanical endurance. Next is a proposed fabrication for soft actuator. So as I said previously, there are several types of soft actuators: shape memory alloy, light, thermal, or pressure, explosive, ionic polymer, and DEA. So for this particular research, I have chosen to choose a DEA because when DEA outperforms every common soft actuators out there, and the most prominent factor that you got to look into is the strain percentage, where DEAs can actually extend or strain up to 1,000%. It has a very high power density, very high strain rate, and a very high actuation frequency. So how DEA actually works is that you have a dielectric membrane being sandwiched between 2 compliant electrodes. So when voltage is applied, it induces opposite charges that results in a Maxwell pressure, meaning it will squeeze in the thickness direction and generates an area expansion. So in practical, this is how DEA actually works when voltage is on and off simultaneously, concurrently. So DEA has several advantages, such as being the best candidate for artificial muscle. It can surpass human or natural muscles that strains that exceeds 300%, high energy density, and low weight and fast response. However, the main disadvantage for a DEA is because it has a high actuation voltage, typically in the kilovolt range. So I propose the use of the development of the low voltage DEA. So one method to reduce the actuation voltage is by reducing the material thickness or the membrane thickness. So there are 4 ways you can reduce the membrane thickness. Typically, a typical DEA membrane thickness ranges from 20 micrometer to 100 micrometer. And to reduce the actuation voltage down to a few hundred, the membrane thickness should be in the range of a few micron. So there are 4 ways you can reduce the membrane thickness: direct manufacturing or pad printing. Number 2, pre-stretching. Number 3, spin coating. Number 4, blade casting. So I've chosen pad printing because it is a commercially available pad printing, and it only reduces the membrane thickness and it doesn't alter any other material property. Pre-stretching, however, it reduces the thickness, but it also modifies the Young's modulus of the membrane. Spin coating and blade casting reduces the thickness, but causes the membrane to possess a breakdown strength that is incompatible for DEAs. So DEA actually performs when you have a very good compliant electrodes, because it depends on the performance of compliant electrodes. There are 4 types of compliant electrodes: carbon grease, carbon powders, ionic gels, and conductive polymers. For this particular research, I've chosen single-wall carbon nanotubes, which is a particular carbon powder that possesses interesting properties. Single-wall carbon nanotubes it consists of nanoscale tubes that are made of carbons, and research has shown that it has superior mechanical strength, high thermal stability, excellent conductivity, and it allows the DEA to actually achieve strain larger than 200%. And through localized degradation, the single-wall carbon nanotubes possess a fault-tolerant property. Under aerospace condition, single-wall carbon nanotubes shows no significant changes in its electrical properties under proton beam conditions. So in conclusion, I can say that DEAs offer a large deformation, quick response, and high density. By reducing the membrane thickness, you can actually reduce the applied voltage down to a few hundred. By employing single-wall carbon nanotubes, you can achieve fault tolerance for the soft robot to locomote in unstructured terrains, have high mechanical strength, high thermal stability, and is able to operate under aerospace condition. So this particular proposed work will actually be a stepping stone and will actually open up new ways for planet exploration using biologically inspired soft robots. Thank you. And these are the reference.
Thank you so much. That was a fantastic talk. We have time for a couple of questions. First of all, how can we actuate these manually over long distances with high precision? Okay, to actuate this manually, you have to use a microcontroller. But over to long distance, it would be a a barrier that we need to actually surpass. Because currently, using microcontrollers to locomote a soft robot, it only lasts about 20 minutes. So for a long distance, this would be another research that need to be dealt with in order to achieve a longer distance or longer traveling time. Great, thank you. We have another one, which is, how would you manage the issue that soft materials can consume small particles due to porosity, which could potentially damage internals?
Okay, for that particular question, the answer is going to be quite long, so I'll just try to answer anyway. So for this type of soft materials, yes, they are prone to radiation and stuff, but there is a limit for it to actually locomote. So like I said, you only can last for a short distance, because according to our current technology, according to the current silicon elastomers that we have, it will not last that long for a longer period of time. So if you compare it with the longer period of time, it does actually prone to if you use it for a longer period in radiation, then yes, it might cause degradation or malfunction for the particular soft robot.
Wonderful. Okay, thank you so much for a fantastic presentation and for answering those questions.
You're welcome, Joshua.
Yeah, wonderful to have you. we will take a couple minutes break ahead of our next speaker.
All right.
So yeah, we'll
Thank you, Joshua. You have a good day. All right.
You too. Thank you.
Cheers.
Hello, everyone, and welcome back for our next talk. We've now got modeling dark matter as antimatter with negative mass and the implications of this model for superliminal travel by Joshua Sinclair. Josh is a recent graduate from the University of Bristol, where he completed a BSc in physics and philosophy with a particular focus on the interaction between philosophy of science and the philosophy of mind. During his studies, he was drawn to the problems faced by any grand unified theory that aims to reconcile quantum mechanics with general relativity, and sought to approach this issue from a wider philosophical perspective, which calls into question traditional assumptions about the nature of time and causality as being necessarily linear. To this end, he has a deep fascination with so-called imaginary numbers and the role that they may play in the generation of wormholes, external reality itself, through superstring theory and Bohemian mechanics, conscious experience and holographic memory, as well as metaphysical implications that arise from such models. So, hi there, Josh. It's great to have you here.
Hi, thank you, Josh.
Thank you so much for joining us. We're ready to go ahead whenever you're ready. So, yeah, take it away.
I'll just share my screen. Okay.
There we go.
You see that?
Perfect.
Cool.
Thank you.
Thank you. Hi, everyone. Yes, so this is my paper on modeling dark matter as antimatter with negative mass and the implications of this model for superluminal travel. So to begin with, here's an overview of the topics of the talk. So I first will start with the problems and questions posed by dark matter and antimatter to the current lambda CDM cosmological model. And then in order to try and formulate a kind of model that can explain these two, the questions that still are faced by these two entities, I'll first look at general relativity and the geometric universe, then turn to quantum mechanics and the EPR problem of causation. And then I'll look for newer kind of superstring theories and non-local theories of the universe and quantum gravity, before then turning to dark fluid theory and negative mass to then conclude by proposing a kind of holographic and quantum version of the Janus cosmological model, and then consider the implications of this on superluminal travel and further philosophical implications that this could have. So first of all, dark matter and antimatter. So what is dark matter? This is a question still being asked by many physicists, astrophysicists in particular. Also, why is there less antimatter than matter in the universe? So in Feynman diagrams, antimatter is modeled as traveling backwards in time in order to be able to exchange the energy required in quantum field theories. And dark matter, the presence of that is inferred from the rotational velocity of the galaxy's edge being the same rotational speed as that of the galactic center, and by gravitational lensing around black holes. So a method by which both dark matter and antimatter are produced, as well as the true nature and full extent of the nature of the identity of each, requires further exploration in any kind of grand unified theory. So first we turn to general relativity and the geometric universe. So the speed of light, I'm sure everyone on this call would know, is the maximum speed that's possible to travel at, according to the postulates of special relativity. Here we've got the famous relativistic mass energy equation given by Einstein. And this shows that as the momentum of an object increases, the p, then so does its mass because of the additional energy being provided on the left-hand side of the equation. So an object accelerated to light speed would appear to require infinite energy and possess infinite mass if it was accelerated to light speed, something with mass. So the question arises, is there any other possible way? Obviously, as achieving infinite mass seems impossible, is there any other way to achieve acceleration relative to space-time? Notably, there are negative mass solutions possible to be derived from that equation by taking the square root. So could there be any link here with antimatter, which possesses the negative charge relative to regular matter and the negative in relation to other quantum numbers to that of matter? So now we'll turn to quantum mechanics, which is the other kind of big theory that needs unifying with general relativity in order to come up with a grand unified theory. So before we explore this concept of negative mass further, let's first turn to the principles of quantum mechanics. So we have within this wave-particle duality, that's probably the most fundamental thing observed in the double slit experiment. And from this, we gain this notion of superposition. Here's the famous example of Schrodinger's cat, where the cat is both dead and alive in the box until measurement, because in quantum mechanics, there's this issue of something behaves as a wave in one instance, but a particle in another. And there's this problem of defining what the difference is between the two states and what causes it and what measurement is. But entanglement is something which allows many classical states to be superposed until measurement, but then during entanglement, because multiple particles can be superposed, this means that because of the Pauli exclusion principle, if two particles are entangled and you measure one, then because two fermions cannot occupy the same quantum state, this seems to create a logical contradiction with general relativity and things not traveling faster than the speed of light with mass, because this process of wave function collapse appears to occur instantaneously when something achieves definite properties during measurement. And this problem led Einstein to write the famous EPR paper, where he asserted that quantum mechanics must be incomplete because it's incompatible with general relativity and it seems to violate a notion of determinism and linear time. And he asserted that God does not play dice. So how do we get around this problem? Well, in 1964, mathematician John Bell proved that local hidden variables of the kind imagined by Einstein were impossible due to experimental evidence that yielded probabilities incompatible with those that would result from if variables were local. This led him to advocate for a version of non-local quantum mechanics called Bohmian mechanics, which was originally proposed by de Broglie. The key difference between this and the Copenhagen interpretation, it's fundamentally that the Born rule is only obeyed sometimes rather than all the time. And this is a Born rule here, which gives the position of a particle as the modulus squared of its wave function. Instead, Bohmian mechanics imagines that imaginary or virtual states that do not obey the Born rule and their position cannot be found from the modulus squared of the wave function. They still exist, these virtual states, and they play a causal role in generating reality. So by this method, Bohmian mechanics introduces a guiding wave equation that allows particles to exist even when they're unobserved and still affect reality and its development. This introduces imaginary wave vectors into the wave function and thereby avoids the measurement problem. In a similar vein, in 2013, Leonard Susskind proposed that two particles that are entangled are actually connected by an Einstein-Rosen bridge, a wormhole, and this is the ER equals EPR theory. And this would allow the seemingly apparent violation of causality because a wormhole has the ability to travel between 2 points in time as well as space. This theory also exhibits ADS-CFT correspondence, which is anti-de Sitter conformal field theory correspondence, which allows for a solution to be found in both general relativity and quantum field theories. So in a way of trying to define this kind of space that such a wormhole might travel through, let's turn now to superstring theories, and which is often portrayed as the best theory that can allow quantum gravity. So the basic tenet of superstring theory is that particles can be modeled as different vibrations of one-dimensional supersymmetric strings that exist at the Planck scale. So superstring theory is a kind of variant of quantum field theory. And there are many dimensions posed in this theory, up to 100, through its utilization of holography. A hologram is something which allows a large number of dimensions to be encoded onto a small number of dimensions, like in a DVD player. So in ER equals EPR theory, holography is used to resolve this black hole information paradox and give definition to the anti-de Sitter that wormholes exist in. In F theory, which is proposed by Kuhn-Waffer, 12 dimensions are theorized to exist. And this is one of the most complete kind of formulations of superstring theory, because there are two 6-dimensional Calabi-Yau manifolds that they compactify when fields exert forces upon them to lower dimensional shapes. So in this way, you can imagine the second Calabi-Yau manifold as a kind of parallel universe, which could potentially, and is theorized in the paper, corresponds to the space where the virtual imaginary particles that feature in Bohmian theory exist. And that in this way, they can be imagined as a kind of tachyon because they exist on their own axis of time, imaginary time specifically, and that allows them to travel apparently instantaneous from our perspective because they're cutting through the time between time, subtime, so to speak. So this leads us on nicely to dark fluid theory, which was proposed by James Farnes at the University of Oxford. And it basically proposes that antimatter exists on the opposite side of the quantum vacuum on the other side of space-time and is the red mass here on the image. Interestingly, in black hole evaporation theory by Stephen Hawking, it's modeled as a virtual particle being produced at the event horizon boundary. So this could be the method by which antimatter is produced in the universe when black holes suck in matter into a kind of anti-de Sitter space. So I'm running out of time. So here is the an image of the holographic quantum Janus cosmological model, because a model of a parallel universe is already theorized to exist by Jean-Pierre Petit in the 1970s. I basically proposed that instead of being parallel, the two are perpendicular, because this would allow for one to be in imaginary time and thereby enable things such as time travel effectively, something which appears to exhibit tachyonic behavior. And this would allow the behavior exhibited by certain craft that have been released recently by the Pentagon. Here's some images of that. And basically, it would enable the creation of Alcubierre drives and warp drives through an imaginary time axis actually existing. And this would require an evaluation of historical and religious claims, potentially, of different unidentified phenomenon occurring if time travel were a possibility and reality were non-local and ultimately composed of wormholes. So there's some further philosophical implications, but I don't think that we're going to have time to go into this because I'm pretty sure I've run out of time. And thank you for listening. Any questions? Perhaps I can touch on the philosophical implications in any questions. Thank you for listening.
Wonderful. Thank you again for coming along, giving a fantastic talk. Particularly interesting to myself as someone who's also just finished a degree in physics and philosophy. We've got one brief question. Well, not a brief question, but we have time to answer one question briefly, which is, how would one go about developing these subliminal drives from our current level of understanding?
Sure. So in the patents that have been filed by the US Navy, I kind of missed out saying that, sorry, but it details a way by which a kind of fusion reactor is developed, which in the patents filed, they were filed in 2016 by Salvatore Pais, and they claim that by creating an oscillating electromagnetic field and through the manipulation of gravitational waves through acoustics, that a negative inertial mass can be achieved, and the achieving of negative inertial mass is what would theoretically allow you to travel through anti-de Sitter space and through these hidden imaginary Calabi-Yau manifolds, because yeah, it's basically you'd have to oscillate it super quickly. So it in the designs, it's a kind of generated by a battery powered kind of piezoelectric crystal that produces these fields that then oscillate really quickly and entangle a lot of particles across space-time by the rapidity of the oscillation of the quantum vacuum, basically.
Brilliant. Well, thank you very much for answering that question, and thank you very much for giving your talk again. It was fantastic and very informative. We'll now take a short minute's break before we move on to our next speaker. Hello, everyone, and welcome back. We now have our final talk before we go for our lunch break. We'd love to welcome our next speaker, George Bell, who will be talking on the gravitational braking of captured moons around ring planets. George is a second-year computational physics PhD student at the University of Lincoln, who previously completed a BSc in natural sciences with the Open University. Hi there, George. It's wonderful to have you. Thank you so much for coming along and giving a talk today.
Oh, hello, and thanks for accepting my paper and all the help you've provided. So
it's our pleasure. We're ready to go whenever you are.
Oh, I'm ready now then. I'll just share my screen so we can see my slides.
Awesome. We can see those.
Are we nice and visible?
Yeah, brilliant. Take it away.
Well, since you've already introduced me, I have no need of this one. In Hesiod's epic ancient Greek poem Theogony, Phoebe is listed as a Titan, one of the gods before the gods and the sister of Saturn, seen here as the figure on the upper right of the fresco. Long ago, the Titans fought the Olympians in a chaotic battle and were cast down into the dungeon Tartarus. This happens to be apt for the captured moon Phoebe, which is thought to have been displaced from a distant orbit in the Kuiper belt to its observed place at the side of Saturn during the instability in the dawning years of the solar system. Not to take a myth or a metaphor too far, we now consider the formal definition of captured moons and planetary rings. The orbits of captured or irregular moons such as Phoebe are like the blue trace in the figure on the left, in contrast to those of regular moons such as the Moon and Saturn's moon Titan, which are more like the orange trace. Irregular moons are stable at greater distances, elliptical or eccentric, and often so highly inclined that they orbit in the backwards or retrograde sense relative to the planet, regular moons, and rings. The red moon in the GIF on the right is an irregular moon in a retrograde orbit. This gives it a high relative velocity with the grey prograde moons and would make for a violent impact if they collided. These features suggest that irregular moons can't have formed with the regular moons. From their composition, it has been suggested that irregular moons like the dark icy Phoebe formed far away from the Sun in sun-centered or heliocentric orbits as minor planets in a region known as the Kuiper belt, as in this picture, and were displaced inwards during a period of instability in the early solar system, when the migration of planetary orbits caused an ice giant like Neptune to be scattered into the Kuiper belt. The timing of this instability remains uncertain and is a subject of debate, but is commonly agreed to be within the solar system's first billion years. It is thought that this instability is necessary to explain the observed solar system because modelling of the formation of the gas giants suggests that they are formed in a compact range of orbits close to the Sun, though they are observed to occupy more dispersed orbits in the present day. The instability is triggered as Jupiter and Saturn cross through a resonance, scattering the ice giants. And you see that this picture includes 5 giant planets. An extra ice giant is considered necessary in newer versions of this model, known as the Nice model, after the city where it's proposed. The reason for this can be seen in the graph on the left, which shows an example of how planetary orbits may evolve over time. The pink line is the innermost ice giant in a 5-planet system, which is ejected from the solar system after circa 10 million years. These ejections are common due to the violence of the instability, hence adding a 5th giant planet increases your chances of finishing with the required 4 planets. Their reproduction of the solar system remains atypical and suggests that the observed structure is not likely. We also see in the graph that the dark blue Neptune is scattered into the Kuiper belt, which brings us back to the inward scattering of Kuiper belt objects. These Kuiper belt objects are commonly found as pairs or binaries. As pictured on the right, if one of these binaries passes close enough to a giant planet, but the planet's tidal force is greater than the mutual gravitational force holding the binary together, the binary will be disrupted, and one or both of its component parts may be captured as moons. From the equation derived during work on Neptune's moon capture, this makes the capture of an irregular moon, such as Phoebe by Saturn, quite plausible. Having considered irregular moons, we now turn to the nature of the Saturn system's rings. A close-up view reveals that the rings are made up of billions and billions of smaller icy particles, which can clump together or accrete into larger bodies up to 30 meters across as shown. These particles orbit in the same direction as the planet. One key feature of the rings is their flatness. Though Saturn's main rings are 270,000 kilometers wide, they are only a few meters thick. By way of comparison, if you scaled up a 12-inch vinyl record to the same width as Saturn's rings, the rings would be less than 1/10,000th the thickness of the record. As illustrated on the image, ring particles which are vertically displaced will still have to pass through the rings twice in each inclined orbit, where they are likely to collide with another particle, reducing their vertical displacement. You can also see that Saturn is a little wider than it is tall, by about 10%, and the gravitational force from this bulge or oblateness will also pull particles back towards the plane. Similarly, another way that collisions contribute to opposing change comes from the reduction of particle eccentricity. Kepler's third law links orbital radii with orbital period. The GIF shows that in our solar system, bodies nearer to the centre take less time to orbit than bodies further out, and this is equally true for ring systems. On the picture, we see that the fast-moving ring particle on a more eccentric orbit moves further away and undergoes a high-velocity collision, causing it to lose its eccentricity again. Now we've seen what the rings are, we can ask how they formed. The current theory is that the material in the rings was originally in the form of a large moon composed of ice and rock partially differentiated into layers. As we see in the image, this moon migrated inwards towards Saturn's Roche limit, represented by the white line. The closer the moon gets, the greater the tidal force Saturn exerts on it, which deforms the moon until at the Roche limit the tidal force overcomes the moon's self-gravity, tearing it apart. Particles nearer to Saturn move faster than those further out, and these particles spread around the planet to form rings. One open debate relevant to my research relates to the age of Saturn's rings. The Cassini space probe measured the mass of the rings and found it to be much lower than expected, at less than half the predicted mass, leading some scientists to conclude they couldn't have survived erosion for any longer than about 100 million years. That still makes them as old as the dinosaurs, but not old enough to interact with moons during capture in the early solar system. However, the apparent age may not reflect the true age. What we see could be the remnant of a massive ring as old as the solar system, formed before the Earth had cooled. Conservation of energy laws require the captured satellite to transfer orbital energy to the existing planetary and ring system as it gravitationally breaks. In my project, I'm using computational modeling in the Python version of the specialist code Rebound to bridge the fields of irregular moons and planetary rings and investigate this entire process in detail for the first time. I've chosen to focus on this specific example of the capture of Saturn's largest irregular moon, Phoebe, due to the wealth of available Cassini data, and as this would serve as a good general test of the situation where a ringed planet captures a large moon. It is thought that this could cause a major vertical displacement of ring material. When this significant change is opposed by oblateness, as shown by the exaggerated oblate spheroid on the left, and collisions as described earlier, this distinctive corrugated spiral pattern is found, which becomes more tightly wound over time due to the shear from Kepler's third law. Similar interactions have been observed. The image on the left shows comet Shoemaker-Levy 9, which was broken up by Jupiter's gravity during a close encounter in 1994. A major influx of dust from this event entered Jupiter's rings, tilting them and inducing the spiral pattern seen on the right. Figure A shows the original image of the rings taken by the Galileo probe. Figure B is enhanced to show the spiral pattern, and Figure C is a graphical representation of Figure B showing how ring slope varies over the radius of the ring. These observations, the dependence on the impactor's approach trajectory, and the time variation raised an application for my work. By observing the shapes of spirals in ring systems now, it could be possible to work backwards and constrain the parameters of a moon's capture, even though the capture itself wasn't observed. Something which has been done previously with a smaller recent cometary impact at Saturn, which took place in 1983 but was not identified until 2011. As with the previously cited paper on Neptune's moon capture, my methodology may be divided into 3 stages, where the results of each stage inform the starting conditions for the next. The first phase is focused on finding statistics for plausible encounters between Saturn and KBOs during the instability. This data may then be used to reproduce these encounters with binary objects, which would enable the determination of a likely post-capture orbit for Phoebe. This orbit may then be evolved towards Phoebe's present-day orbit to determine how Phoebe interacted with the Saturn system, and in particular Saturn's ring system. This last phase may differ from the case at Neptune, where tidal forces have circularized the orbit of its irregular moon Triton, and reduced its semi-major axis to a much greater extent than is seen for Phoebe, where alternative forms of evolution, including collisions with other irregular moons, may prove more significant. And so to conclude, we return to our original question: does the capture of minor planets around gas giants change ring structures? It's a significant open question in planetary formation and evolution, relevant to both our own solar system and to the study of exoplanets. This video is one answer, but it's a completely unrealistic one. We don't yet know what the realistic scenario would look like, and the aim of my project is to find out. Thank you.
Thank you so much, George. That was fantastic and greatly enjoyable.
Oh, thank you.
We have one question for you before we go into our lunch break, and that is what extra data, if any, is needed in order to create a comprehensive model of the rings to reproduce and forecast events?
Comprehensive model. Well, the temporal element is quite a significant one. Part of the value we had here is having probes at the ring system, which were able to observe how it changed over time. That's a particularly significant example from Cassini. Obviously, as Cassini's measurement of the mass has been hugely informative for this process, and it's proved significant. The mass of the rings is quite significant for a rather broad variety of problems. It even has bearing on the origins of the mid-sized moons of Saturn. So, which is something that I elaborate on in my paper. I think we're considering here mostly what takes place in the C ring, where these corrugations have been witnessed, which is one of the 3 main rings of Saturn. So, yes, a comprehensive and temporal coverage of the main rings of Saturn is something that would be highly valuable here. Okay,
brilliant. Thank you very much.
Thank you.
A fantastic answer and a fantastic presentation. If any more questions maybe coming throughout the day, I'll make sure to send them your way, if that's all right with you.
That's fine.
Okay, and thank you very much. for submitting your paper. Congratulations on being selected for the symposium, and thank you again for a wonderful presentation.
Thank you.
So now we're going to go into our lunch break, which is going to last an hour until 2 o'clock. And after that, we'll have a sponsor talk from Astro Agency. I highly advise you, if you have some time over lunch, to go and check out our careers fair, which you can see on the sidebar of the Nebula platform on the right side of your screen, where you'll be able to join the stands of our sponsors. Be a great idea to go and chat to Astro Agency about the wonderful things they do and opportunities with them ahead of their talk after lunch. So yes, I'll see you in about an hour. Thank you very much.
Good afternoon, everyone.
Hello, everyone, and welcome back to the UKSEDS Student Space Symposium. I hope you had a very enjoyable and restful lunch break. To kick us off just after lunch, we're going to have a talk from one of our sponsors, Astro Agency, who you can also go and speak to live today in our virtual careers fair, which you can access on the right-hand side of your screen in the sidebar of the Nebula platform. Just a bit of information about Astro Agency before we start. Astro Agency were the first space-focused marketing agency in the UK. They provide innovative companies with the strategic guidance to thrive in the new commercial space market. Their expertise is perfectly suited to assist anyone looking to grow their business in the space market, from space and non-space companies to industry groups and organizations that represent the wider interests of the space sector. We'll now go over to them for their sponsor talk, and I hope you enjoy it.
Good afternoon, everyone. I hope you've all been enjoying this conference as much as I have. I'm Anastasia. I'm one of the marketing executives for Astro Agency. And today I'll tell you a little bit about Astro Agency, my role, and our popular networking event, Space Bar. So what is Astro Agency? We are a leading strategic marketing firm operating in the space sector. At the moment, we have 9 staff in 5 different countries and are currently looking to expand our team. We've always been working remotely, not just in the pandemic, allowing for such a multinational and diverse team. Our clients, as you can see, a little snapshot down below, represent the whole global value chain and range from startups and existing space companies to bigger corporate organizations wanting to break into the space industry. Astro Agency provides a range of services, with one of our main strengths being the connections and networking introductions that we help our clients with. With the space industry being at the cutting edge of humanity's development, it may come as a surprise to you that there's a significant gap in marketing. And this is where Astro Agency comes in. We help innovative minds keep their focus on developing new technologies by using our team's expertise to propel their story across the globe and commercialize their offering, or just find customers or investment. What is my role? Within my marketing executive duties, I wear many different hats. I help look after First Step Legal, which some of you may know, and work with Daniel, our creative director and founder, on Space Cornwall. I also look for new business at conferences, but my main role is managing Spacebar. Spacebar was initially developed to help bring people together on Thursday evenings during the nationwide lockdown. Astro Agency wanted to create something really unique without the typical webinar feel where everyone could really get involved, network, and feel less isolated at home. This unique format really took off, so we decided to continue Spacebar after lockdown and have had so many interesting sessions with great people. Some of our regulars even stay until the early hours in the morning. Dallas Campbell, a TV presenter and author, is our main host. And Susie Imber, who you guys might know from the Astronauts Do You Have What It Takes program, has been a great recent addition to our Spacebar team. With their knowledge and great insight into the space industry, they really make every evening really interesting. Spacebar is known for being the drinks reception of space webinars due to the laid-back, fun, and interactive nature of this online event. We have had some amazing turnouts, with the record being 100+ industry reps. And we've also had prestigious guests such as the Swedish Space Corporation, the ESA ambassadors, and ESA business incubation networks join us for Spacebar. So going forward, what can you take looking at Astro Agency's approach to developing Spacebar? So we would suggest analyze how COVID has changed your normal working process, and then take any positive aspects that you have found or you have experienced in this difficult time. And as we did for Spacebar, try and include platforms in your promotional strategy. And last but not least, come to Spacebar. The drinks are on us, as we're always looking for interesting moderators to moderate any of our panels or just to join in any discussions. So here's a QR code that feel free to scan it. It will bring you to our Spacebar registration page. We have one for not next Thursday, but the Thursday after that, as it's a sort of bi-weekly event. Also, feel free to reach out to me via email, follow us on Twitter, and don't forget to sign up for Spacebar. Thank you very much for listening to me.
Hi everyone, I hope you very much enjoyed that talk from Astro Agency. As I mentioned briefly before the talk, if you'd like to talk to them in person, talk to them about the wonderful work they do in the UK space industry or potential career opportunities with them, you can join the queue for their virtual careers fair stand on the sidebar of the Nebula platform. So please make sure you go along and speak to their company representatives at some point throughout the day. Our next talk is coming up at 10 past. So we will now take a brief break until then. Hello, everyone. Welcome back for our next talk. We're now going to be hearing from Dhruv Singhvi on his paper, Societal Structure of an Intelligent Extraterrestrial Species. Dhruv is a student at the University of Leicester. So, hey there, Dhruv. It's great to have you. We're ready to go ahead whenever you're ready.
Oh, sure. Yeah. Is it fine?
We're just waiting for the presentation.
Is it live now?
We can't see your slides.
Oops, sorry. Yeah, I'm sharing it now. Yep. Is it live?
No, we still can't see them, I'm afraid. However, if you'd like me to share the presentation myself, and then when you're ready to go to the next slide, I'd be happy to do that for you.
Yeah, sure, that will do.
Sure, I'll quickly get that ready for you.
Yeah, thank you.
Okay, brilliant. We're ready to go. Just let me know at any point throughout the presentation when you'd like to progress to your next slide.
Yes, sure. So hello, I am Dhruv Singhvi, and my topic for this paper is Societal Structure of an Intelligent Species. Next slide, please. So in an overview, what does the paper say is that the paper defines an evolutionary system which might have the potential to give rise to a human-like species. And also with that, it also discusses some features of their societal structure. Next slide, please. So we all know the traditional question of, are there any other human-like species in the universe? And as we might know that it has troubled many philosophers and scientists over the millennia. But in this paper, we use a slightly different approach of asking, are there any other evolutionary systems that can result in human-like species? So, well, we started to analyze this question, and we reached the conclusion that, next slide, please. That, yeah, well, yes, maybe, yes, there are other evolutionary systems that can give rise to human-like species. So, next slide. So to start with the basics, to understand how did we reach to that conclusion, let's start with the basics. The basics is the fundamental property of life, which is information transfer. And acquisition and transfer of information from one generation to other generation is what we call as the universal property of all life systems. So next slide, please. So we would use this property to define a new scale called as the information scale. Now, what this scale does is that it categorizes life species into different levels, which are based on how and what information do they transfer with each generation. So as in, we have the level 1 species, which transfers simple information using the basic unit of life. On Earth, it's genes and DNA. On some planet and some other systems, it might be different. In level 2, we have the simple adaptive solutions, which are formed by the simple different interactions of unit of life. And the level 3, which we have called the intelligent species in our paper, and it has the potential to give rise to other human life systems. And level 4 is an advanced version of level 3, so to speak. Next slide, please. So let's define what is a level 3 species. Well, a level 3 species is a species which would be able to transfer both the inherited adaptive solutions along with externally acquired traits from the surrounding. So to understand this, it's like saying a human if a human is in a level 3 species frame, then the person would be able to transfer not only the genetic material, but also the traits which have been acquired during the person's lifetime to the offspring. Now, as you might see, that it has a greater advantage of to the offspring of being more adaptive to different surroundings and the environment. So, like the whole system is encapsulated by a level 3 species. Next slide, please. So the question of how would it be able to to give rise to human-like species? Well, to answer that, we have to consider that the traits acquired by the parent in the lifetime, which would be inherited to the offspring to solve more and more complex problems, more problems where the survivability and the reproductive success of the individual would be enhanced. So these externally acquired traits by a parent would be like a head start for the offspring. And as time goes, this traits would have a compounding effect, like as in all generations are adding their own externally acquired traits throughout their lifetime. So this would give rise to more and more complex species within a short duration of time. So if given enough time, it might have the possibility of evolving into a human-like species. Next slide, please. So let us discuss about if they ever evolve into, well, one of those species, then how would the society look like, or discuss the societal structure. The reason why life systems have evolved societies on humans and in groups, it's because they provide a very effective way of solving complex adaptive problems. Well, when considering groups, we have to consider three important things that are, well, coordination within an individual of a group, coordination with other individuals of the group, and the means by which they're coordinating. Next slide, please. In human society has solved these problems, these three group problems, by having emotional systems and hormone systems in our biology. Coordination with other organisms, well, it's an extension of social behavior, and for means of coordinating, we have language, facial expressions, and non-verbal communications, etc. Next slide, please. But so as an extension for that, we hypothesize that for a level 3 version of a species, it would have these following systems to solve those problems with considered to group formations. And these are, well, the same cause. For first, which is the coordination within organism, it would have a chemical based system considering the reliability it has on Earth as well. The second is the coordination for other organisms, and we expect the existence of subgroups based on similarity in traits. And good analogy for that would be the existence of the different races on Earth in terms of humans. Then for the means of coordination, it might be some form of energy transfer. Well, the basics of life is that life and energy goes hand in hand. On Earth, it's when considering humans, it's the sound energy, whereas it might be different for others as well. Next slide, please. And since it's just a theory based on it's based on Lamarckian inheritance, because a level 3 species basically a Lamarckian system fused with Darwinian evolution. These are the assumptions that it has to take for it to work. So, yeah. Thank you for that.
Thank you so much. That was a brilliant talk.
Oh, thank you.
We currently don't have any questions in, but if any come in after, after the presentation or throughout the rest of the day, I'll make sure they get forwarded to you. Sure. But yeah, thank you so much for your presentation and for joining us today.
Thank you so much. Yep.
Oh no, hold on. We do have one question before I send you off. Lucky you. Which is, it seems that you have claimed that communication is essential for the intelligence of a species. Is there sort of any basis for this?
Well, it's cause it has an important basis because there are three things when considering groups, right? How the individual performs, how it's connected to other individuals, and the method by which the individual is connecting to other individuals. So another way of describing the third one is basically language or communication. Now, when considering human systems, we have languages, but when considering other systems is in, well, the animal kingdom, they have other systems, be it different colors on the color representations or the mating calls or the sound systems for different birds as well. So intelligence does play an important part. Communication does play an important part for communication, and we have described it more in the paper. So it was just an overview here as well.
Brilliant, thank you. And the next question is: are there any other assumptions that you've made in this paper, and can you talk more about them?
Well, the assumptions are just that it's the same because the only place in the universe we know there are life systems, it's on Earth, right? So the assumptions are mostly that, well, if humans have to, a human-like species have to evolve, it has to be more on the basis of information, because even in the paper, humans are is a species between level 2 and level 3. It's not on the level 5 of the things, biologically speaking. But because of communication within humans, we have reached a level 5 species. So like, it's not just because of biology, we are at level 2 and level 3. We are not ahead in any way because of the communication we have done it. So yeah.
Thank you. Two brilliant answers to those questions. And as I said before, a wonderful presentation. So thank you very much for joining us today. We'll now take a couple minutes, quick break if anyone needs to stretch your legs or grab a drink ahead of our next talk.
Sure.
Hello and welcome back for our next talk, which is Near Field Acoustic Levitation and Hypergravity by Alexander William Pryor, Joachim Wilhelm Hendrikus Langen, and Juan Paulo Lorenzo Gerardo Barrios. A bit about our speakers and authors. Alexander is a third-year integrated master's student at Durham University, studying physics and taking modules in condensed math physics and planets and cosmology. He's currently the team leader of the research group working on a project to investigate near-field acoustic levitation and hypergravity conditions for the European Space Agency Academy. Joachim is a third-year integrated master's student at Durham University, studying physics and astronomy and taking optional modules in theoretical physics and planets and cosmology also. He's currently one of the core members of the research group working on the same project as Alexander. Paolo is also a third-year integrated masters at Durham, taking the same modules, and a core member of the same team. So thank you guys for joining us so much, joining us today. Really appreciate it. We're ready to go as soon as you are.
Great. I'll share my screen then. Does that work?
Yep, that's perfect. Thank you.
Great. Okay, let's get going then. So good afternoon, everyone. My name is Paulo Barrios, and together with my colleague Joachim Langen, we are members of the ESA team known as the Levitators, and today we'll be giving a brief presentation on our paper entitled Near-Field Acoustic Levitation in Hypergravity.
Yeah, so first of all, we start off talking about the different ESA gravity-related programs, followed by what near-field acoustic levitation is in general. Then we'll talk about our general setup, and then a specific part of that, the transducer and the ultrasonic stack, followed by the microcomputers, and then the data correction that comes along with this experiment. Then followed by the NFEL, or near-field acoustic levitation models, and finally the benefits of the ESA program.
So to start off, we want to give a few words about ESA's gravity-related programs. So these are programs available to students. As I mentioned earlier, we work in the Spin Your Thesis program, which is a program where students are allowed to put their experiment in ESA's 8-meter diameter centrifuge to simulate hypergravity. Here, there's also a Fly Your Thesis program where you get to fly your experiment on a parabolic flight to simulate cycles of high and low gravity. Drop Your Thesis program, where you get to drop your thesis in a free fall tower. Orbit Your Thesis, where you get to orbit your thesis literally on the ISS. And Spin Your Thesis Human Edition, where your thesis is put similarly in a large diameter centrifuge, but you can have human subjects, essentially. Now, to give a brief overview of near-field acoustic levitation, as the name suggests, it is the act where you can levitate something close to a levitating surface on the scale of micrometers. So how it works is you have a vibrating object here, which emits standing waves, as you can see in this nice picture. And near the center, the waves are fairly stable, so you can have an object levitated fairly stably near the center. Now, this phenomenon has been observed for a while, but we've been using multiple theories, different assumptions, different circumstances to kind of explain how it works. And part of what our project wants to do is to test this NFAL phenomenon under hypergravity conditions to see which theory actually works best in this kind of unexplored regime, and to kind of figure out if there are other unexplained phenomena that we might be able to observe. This particular phenomenon is useful for non-contact bearings, for assembling very sensitive devices, and for transporting objects across surfaces with very little to no friction.
Yes, so our experiment itself consists of two main setups. The first one you can see on the left, where we measure the force profile of the radiating surface above it. Now we do this by using a load cell, which is attached to a stepper motor system, so moving that up and down and then measuring the forces for different amplitudes of the acoustic system. Now on the right, you see a different one where we have a free-floating object, and we've measured levitation height of this object with a laser. Now both of these systems are enclosed in a frame, which is then to be placed in a large diameter centrifuge. And both make use of dampening materials to reduce the vibrations induced by this LVC.
Now, to kind of generate the vibrations needed to induce NFAL, we describe in our paper an ultrasonic stack. A key component of this stack is the actual transducer itself, which we designed ourselves using finite element modeling using a software known as COMSOL. Now, how this works is basically we have an electrical current that goes into a microcomputer, which then tells this transducer to produce a certain vibration. In fact, we want 20 kilohertz vibrations up to 4 micrometers in amplitudes, which is based on past papers is the type of vibration that you need to induce this NFAL phenomenon. Now, to kind of give you an overview of the type of electronics and the setup involved in our experiment, we produced this little diagram here. So we have the ground station at the centrifuge, which is where we will be situated in. In the center of the centrifuge will sit our power supply and most of our kind of big chunky pieces of equipment. Halfway between the experiment gondola and the center of the centrifuge, we will have a power supply and some cables. And in the experiment gondola itself, obviously will sit our experiment. That includes the sorbutane sheet, the metal frame, the vibration system, which is the ultrasonic stack, the linear actuators, which will move the levitated object up and down, the sensors to collect data, including environmental sensors and sensors to measure the force and the height of the levitated object. These will all be connected to a microcomputer, which is linked to the laptop in the central gondola.
Okay, so once we have all this data, an important part of this is data correction. Now, first of all, during the experiment, calibration is very important, particularly because we're working at different hypergravity levels. Now, at these different levels, we get things like that. For instance, the voltages that were used for the ultrasonic spectrum to create certain amplitudes, they change. So we need to recalibrate that, as well as, for instance, the bending of materials due to the gravity strain. And now there are various other environmental factors which change over time, and which, as Pano mentioned, we have various sensors for, such as barometers, thermometers, and hygrometers. Now, using the data from these sensors and the various theoretical models, we can essentially get data to compare this to what we actually measure and essentially correct it in that sense. Now, aside from that, all these sensors that we use, and it's mainly important for the main sensors, so the laser and the load cell, and these have various uncertainties which we hope to minimize to increase our accuracies. Now, this includes non-linearity, non-repeatability, hysteresis, creep, and recovery. Now, by investigating our sensors beforehand, we can essentially create a model for things like non-linearity, to which we can then correct our data. And there are also things like creep and recovery, where, as you can see on the graph on the right, when you apply a certain load or you remove a certain load, so you're able to take time to converge to the final actual value. Now, this can be on quite large scales, and you get things like graying, where the output oscillates until finally converging to the required, to the actual value. Now, by being able to correct this, the data for this, we can make sure that the data is more accurate that we end up with, and that we can take quicker measurements, essentially, which can be important when we work at 20 kilohertz vibrations. Now, as mentioned before, there are various theories which describe NFEL. Now, aside from just NFEL, there's also what we call FFEL, so that's far field acoustic levitation. Now, the difference there being that at half an integer wavelength of the radiating surface, NFEL turns into far field acoustic levitation. Now, these regimes are essentially governed by various theories, and you can in part group them by squeeze film levitation, acoustic radiation pressure, standing wave acoustic levitation, and single beam levitation. And now, these groups themselves, as well as within these groups, use various assumptions and approximations and different ways of deriving them, so using different fundamental equations through which they essentially differ in that sense. So by investigating in hypergravity, we hope to see what essentially works best, and that is by looking at the force profile, where essentially differences between LFL and FFL and how different theories compare over that distance. Now, something that has been investigated before, but it's not really well understood yet, are attractive forces. Now, these may arise at certain frequencies and certain circumstances, where instead of repelling the object away from the radiating surface, it actually pulls the object to it. This, for instance, can be used in microassembly. This is something which, if it will be present, we hope to investigate. Now, these theories we model using a program called COMSOL, from which we can collect data. Now, an image has been shown earlier, which essentially are results from that program.
Okay, so moving on to the actual benefits of these ESA programs. First of all, we have the entry to the space sector, which is obviously the main benefit. As students, we don't really have access to kind of large diameter centrifuges and parabolic flights. And these are the type of things that ESA can provide to us free of charge. In fact, they even give us more money in the form of grants together with the UKSA for us to spend on acquiring our equipment, assembling everything, testing everything, and making sure that everything goes smoothly. In addition, we also have access to expert advice from our mentors at ESA, and also from people from the European Low Gravity Research Association, or ELGRA. And these people tell us everything we need to know. If we have any questions, if we have any doubts, any inquiries regarding which method to use, they tell us what to do. So it really helps us kind of further our understanding of our own project. Aside from that, joining ESA's programs also allows us to form a network of young space researchers. People from other programs aside from Spin Your Thesis, we regularly communicate with them, we exchange ideas, and this will help us later on if we decide to join the space sector. if we already know people inside, it makes the entire process kind of much easier.
So aside from that, there are lots of skills that we learn through this program. Now, these can also be soft skills or more specific skills. Now, this can be either from aspects which we would normally not even encounter in projects in our undergraduate physics degrees, or these are things which we would not have encountered on this scale. Now, this, for instance, can be time, project, and risk management, which is a big factor in a project that lasts as long and involves as much equipment as this. There are other things like sponsorship acquisition. With that also comes public relations, where we have to do things like make a website and manage social media and so on. Now then, there's the budgeting and with administrative, legal, and financial matters that we need to be sorted aside of research that you wouldn't normally really see, aside from a project like this during our degrees. Again, as well, with a budget much larger than what we'd otherwise be able to have access to. Now then, there are more specific skills, essentially learning different programming language and doing a lot more electrical and mechanical design, as well as general systems design for a more intricate experiment. And then finally, there are more opportunities essentially that this program, aside from the experiment itself, gives us access to, such as publication and presenting at conferences such as these. And finally, we'd like to thank some of our sponsors, being ESA, the UK Space Agency, Health and Sensors and Controls, Durham University, and Novatech Low Cell Design and Manufacture.
Great, and that brings us to the end of our presentation. Thank you very much for your attention, and we will now start taking questions.
Thank you. That was a very, very good presentation. Greatly enjoyable. We do have a couple of questions. The first of which is, could you explain some of the future applications of near-field acoustic levitation?
Sure. So basically, all near-field acoustic levitation is it kind of allows you to control an object physically displacing it without actually touching it. And kind of from this statement alone, you can kind of think of how you could use it. So as we mentioned before, non-contact bearings. If you need to assemble very fine devices that are very sensitive to touch, if you need to move something without inducing a static charge, things like this, it's very useful to have this kind of method of moving stuff around without actually touching it. And obviously transporting stuff, it's probably much quicker, although it hasn't been investigated in much detail. If you can move stuff around similar to magnetic levitation trains, if you can do the same thing using acoustic levitation, I imagine that would be very useful as well.
Thank you. We've got one more question, which is, do you have a wide variety of STEM and non-STEM backgrounds and other non-traditional academic backgrounds in the team, or is it predominantly physics-based?
So I'll answer this one. So actually, our team, being actually relatively small, so we only have 3 members, we're all essentially rather similar in that sense. So we all do physics at Durham University. Now, you do see within these programs that you have many different STEM backgrounds, usually it being STEM. Our team just happening to be all physics, but it's essentially with the gravity research, that's quite an area where different subjects actually come together, which is quite nice to see. So there are many different opportunities there.
Wonderful. Thank you very much. Thank you again for the presentation, for joining us today, and for answering those questions for our attendees. We'll now take a quick minute's break before we go into our next speaker. So stay tuned.
Thank you.
Hi everyone, welcome back from our next talk, which is by Eva Bevas, and it's an investigation of collision and disruption events using a direct M-body simulation. Eva is a third-year maths and physics BSc student at the University of Bristol. She grew up between France and England, learning various languages along the way, such as Russian and Polish. Having completed her work experience at the Observatoire de Meudon, Eva aims to pursue a career in scientific research whilst being able to meet and work with people from all over the world. It's a pleasure to have you, Eva. Thank you for joining us today. And I will quickly share your presentation so that we can get right into it. And yeah, whenever you're ready.
Cool. Well, thanks a lot. I'm going to be talking about an experiment I did where I tried to determine the radius and density of comet Shoemaker-Levy 9 from simulations that I did. And along the way, I got to study loads of other parameters such as coefficient of restitution, particle radius scaling, particle number, all other parameters and how they affected collision and disruption events. So I got to make cool pictures like that, basically. Can I have the next slide, please? So yeah, this is a comet Shoemaker-Levy 9. So it was discovered in 1993 when it was already disrupted, as you can see in like 20-odd fragments. And this is a really common benchmark situation in simulations because we know what happened is well documented. So it's quite useful to use something like that to run simulations to see if what we're doing is close to reality. Could I have the next slide, please? So why do we want to study comets and asteroids? Well, they're kind of leftovers from the formation of our solar system. So they haven't changed a lot since then, and their composition as a result is very useful to know how exactly our system was formed. And why would we want to know that through simulations? Well, we could send a probe there and like bring back samples to analyze, see how they made, but that's very expensive, takes a lot of time. It's not something that can be done very fast, realistically. So otherwise we could just map their trajectory through the sky, and that could tell us a bit about their bulk parameters and roughly what they look like. And we can also take pictures, obviously. So that'll tell us about the exposed layers. But again, it won't tell us much about what it's made of, what kind of structures there are inside. So yeah, so that's why we like simulations, because we could test out loads of different scenarios and see which one is more resembles most reality. So could I have the next slide, please? Oh, and the next one, actually. Yeah, so how do we model these comets? So we do something like the picture you can see on the left. So this is a rubble pile. So it's just a fancy name to say loads of little particles in a pile together, basically. But this isn't just something we do for simulations. There's actual evidence that this is what comets actually look like on a more fundamental level. So for example, on the right-hand side, you can see asteroid Mathilde. And the craters that are photographed on the surface are actually too big. So an impact that size would have shattered a rock if this was just one rock. But clearly the rock wasn't shattered. So most probably asteroid Mathilde is a rubble pile, and probably a lot of other asteroids and comets also are. So could I have the next slide, please? So how exactly did I model what I modeled? So firstly, I modeled collision events. So I took a program called RPG and created a rubble pile. This rubble pile, I then put it into another program called RPX, which just set up an initial situation. So it gave them initial position, initial velocity. I could add as many paths as I wanted. So here I only added 2 going towards each other, so in the collision path. And I took this initial situation, fed it into PKD Grav, which is a gravity simulator. And this evolved the initial situation in time. So I created cool pictures like that, and then I could analyze this and see how different parameters affected the outcome in the simulation. So could I have the next slide, please? And what did I find from these collisions? Well, the first thing I kind of varied was a parameter called particle radius scaling. So it's just a fancy name to say how much void there is between the constituent particles in a pile. So if it's 1, it means they're very tightly packed and there's no void basically. But if I reduce it a bit, then I add a bit of space between them in the pile. So for example, here on this picture, it's 0.5, so there's quite a lot of void. And I found that if you increase the particle radius scaling, so that means they're more tightly packed, this increases energy transmission, which again kind of makes sense because they're very close together, so they can easily hit nearby particles, so transmitting kinetic energy. And this, as a result, meant that there were more stray particles. So what I mean by that is, if you look at the last picture on the slide, so T equals 200, those two initial rubber piles went towards each other and then like rebounded. But there's some particles that didn't rebound. They kind of went, everything that's in the middle kind of went its own way, and that's what I call stray particles. So there's more of them, the more tightly packed the initial pile was. So could I have 2 slides forward, please? So yeah, oh, another slide actually, please. So the first piles you saw were made of 85 particles. So these piles are made with 391. So there's more particle in each pile. So what this did is that it increased computational time. So again, there's more particles, so it takes longer to compute. So that makes sense. But actually, when you increase the number of particles, it doesn't change the general shape of the outcome. Again, you can see generally it's again 2 cores that kind of rebound off each other, but it does increase the number of stray particles. Yeah, and the final parameter that I modeled, so if we could add the next slide, was the coefficient of restitution. So this is a parameter that tells you how much kinetic energy is dissipated in the collision. So in the previous slides, they were 0.8 was the coefficient of restitution, so that's very high. 1 means that no energy is dissipated. Here it's 0.4, where 0 would mean that all kinetic energy is dissipated. And I found that, so when you decrease the coefficient of restitution, you actually decrease the amount of stray particles that are created at the end of the simulation. And again, you can kind of think of it as, well, because they're within very few collisions, they would have basically lost all their kinetic energy. So they don't have enough energy to go off to infinity anymore. They just kind of stay within those piles. So all these collision events, this was kind of a preamble to the Shoemaker-Levy 9 simulation that I did. So that's on the next slide. So that's modeling now disruption events. So previous one was collision events specifically. This is disruption events. So it's very similar how I did it. Again, I created a rubber pile with RPG. But now to create the initial situation, this is where it changes slightly. First, I calculated something called the Roche limit. So that just tells you the distance from Jupiter at which the pile is disrupted. And that's kind of roughly related to the ratio of Jupiter's density to the pile's density. I then took NASA's Horizon tool, which kind of looks at a lot of objects in the sky and catalogs them, where they are, when they are, what velocity they're going at. And I can see exactly at what point Shoemaker-Levy 9 crossed the Roche limit that I just calculated, which happened to be between 6 and 9 on the 7th of July 1992. And so I just took the values for its position and velocity a couple hours before then, arbitrarily I took 10 a.m., just to then give the system time to evolve within my simulation, which I did again through PKD Grav. And I got more cool pictures, which you can see on the next slide. So yeah, this is an example of one of the simulations I ran and what I got out of it. So it's good because it looks like what I showed you on slide 2. So it is apparently quite similar to reality, which is always good after hours and hours of compiling simulations. So yeah, this is something we call a string of pearl formations, just because it kind of looks like a string of pearls. And what I did from that, I basically quantified 2 things. The first thing was how many pearls I created. So particularly on this example, you can see it goes from A to Q. So that's 17 pearls. And the second thing that I quantified, which you can see on the next slide, is how long this string is. But again, where do you start the string? Where do you end the string? How exactly do you know what length it is? So to do that, I created an upper bound and a lower bound. So the pearl spread was my lower bound, which is basically the distance from A to Q, if you imagine this picture. And then the largest spread, I did it from, you probably can't see it because it's too small, but there's little particles past A that just kind of shot off right at the beginning of the simulation. So that's my largest spread if you take from the two extremes. And the actual spread is probably somewhere between, if you look at the right-hand side on the graph, somewhere between those two lines. So specifically, that graph is showing you how the length of the string varied with the initial bulk radius of the comet that I modeled. And it actually turned out that bulk radius was the determining factor in how long the string was. It wouldn't be density, it wouldn't be coefficient of restitution, it would be bulk radius that would determine then how long the string was. So then can we have the next slide, please? Yeah, so other things that I varied coefficient of restitution. That didn't really have much of an impact. It just changed how violent and chaotic the initial transient phase of the disruption was, but it didn't really change the outcome. Particle number equally didn't change. But if we see on the next slide, the determining factor was the bulk density of the initial pearl. That was really what told you how many pearls you would get. Yeah, so from that, I kind of determined that the bulk density of Shoemaker-Levy 9 had to be between 200 and 700 kilograms meters to the -3. That was from the number of pearls, and from like the spherical and uniformity of the pearls, that the radius had to be between 550 and 950 meters. Yeah, that's kind of what I found. That's what I did with my summer. Maybe you guys had a more interesting one, but yeah, that's all from me. Any questions?
Thank you. That was another wonderful talk, and I'm certain a great way to spend your summer. We do have a couple of questions. What are the limitations of the simulation, and how could this be extended with more data?
So definitely, I think one of the biggest limitations was the interconnectivity of the different parameters. So I tried to vary to get like a base situation and then vary through a range of like radius, for example, but keep all the other ones the same. But really what you find, so for example, the range of values I said Shoemaker-Levy 9 could have had, is the length of the range is really due to the fact that I did not have the computing power to see how all the different parameters change with respect to each other. And really, yeah, I think that's what you would have to do more of to get a more accurate result.
Sure, we'll get you on one of the NASA supercomputers in no time soon, and then we'll, have a much more wide-ranging simulation.
That would be great.
So thank you very much. We don't have any more questions, but again, thank you for answering them, and thank you for a fantastic presentation.
Well, thank you for having me. Have a good day.
You're very welcome. You too. We will now take another brief break as we wait for our next speaker. Hi, and welcome to our last talk before we go for a short break. We have a talk on urban tree monitoring for space using deep learning architectures to monitor urban vegetation distributions with hyperspectral imagery by Ben Kander. Ben is a recent University of Bristol graduate in physics who has just enrolled at Cranfield University's master's degree in astronautics and space engineering. Having completed a summer internship with the Open University in using artificial intelligence to identify and classify urban vegetation, he's presenting research on the suitability of neural network architectures for use with satellite data to classify urban land cover types. A fan of all things space, Ben is looking to pursue a research career in rocketry or human spaceflight. So thank you for joining us, Ben. We're ready to go ahead with your presentation whenever you are.
Great, thank you very much for having me. I'll just share my screen now. Let me know if you can see this. Is that working?
That's all working. Take it away.
Let me just... There we go. Okay, so great. Hi, everyone. As Josh said, my name is Ben. I'm currently studying astronautics and space engineering at Cranfield University, along with Josh, actually. And I'm going to be presenting research on using deep learning for urban vegetation monitoring from space. So throughout the presentation, I'll give a brief overview of the motivations for the research. I'll do a very brief introduction to the concept of artificial intelligence and convolutional filters. I'll give an overview of the data sets used to train the models and an overview of the model architectures themselves. And then finally, I'll finish with the results and conclusions of the research. Okay, so first off, why do we actually want to map the locations of urban vegetation? So urban vegetation actually provides a range of very important ecosystem and societal benefits, such as natural air filtration, heat dissipation. So for example, tall trees have been shown to reduce local air temperatures by as much as 7 degrees C during heat waves. They also provide humidity regulation, they promote physical activity, and have even been shown to improve mental health. So research has actually shown that specifically tree canopies have been shown to reduce the incidence of psychological stress by as much as 30%. But however, interestingly as well, other types of low-lying vegetation, such as grass or shrubs, actually had no significant effect. So the real take-home message from this slide is that not only is the amount of vegetation and the location really, really important, but also the species and the type of vegetation is important for quantifying the benefits. Okay, so just a brief introduction to artificial intelligence. So in a nutshell, artificial intelligence is the theory and development of computer systems able to perform tasks normally requiring human intelligence. So basically, designing computer algorithms to perform tasks that would usually require some kind of human input or supervision. There are many different types of artificial intelligence algorithms and machine learning algorithms, but this project focuses on neural networks, also known as deep learning. I think this is the most exciting area of artificial intelligence because it's actually modeled after the human brain. So I haven't got enough time to go really into the details of exactly how neural networks function, but the really important concept is convolutional filters for this study, which are used in convolutional neural networks, also known as CNNs. So convolutional filters are very, very good at recognizing shapes and patterns in images. So just to kind of describe exactly what I mean by that, I've got a very brief example at the bottom of the slide here of a convolutional filter in action. This is actually what's known as an edge filter. So in the bottom left here, we have a grayscale image of 3 by 3 pixels. And just to the right here, we have the same image, but in numerical form. So negative numbers represent very bright pixels. Positive numbers represent dark pixels, with -5 and 5 being the minimum and maximum respectively. So here's our convolutional filter just here. It's a 2 by 2 grid of numbers with -5s on the left and 5s on the right. And the way we actually apply this is we just apply it over one section of the image at a time. So I've just kind of extracted this section of the image just over here to make it easy to see. And what we're doing is multiplying the numbers corresponding to each pixel by the appropriate numbers in the convolutional filter. So for this particular example, it'd be -4 times -5, and then we'd add to that -3 times -5, and then adding to that 5 times 5, and then +4 times 5. And that gives us 80 in the output section. Now, what you'll notice here in this particular example is both of the negative numbers in the convolutional filter are multiplied by negative numbers in the pixel values to produce positive outputs. And the positive numbers in the convolutional filter are multiplied by positive numbers from the pixel values to also produce positive outputs. And we end up with quite a large number in the output section. So that's going to be, that's actually quite significant to how this works, and I'll explain exactly why in a moment. So after we've done this section of the image, we then slide the filter over to the next section, so at the top right, and perform the same calculations to get -10. And then the bottom left and the bottom right. Okay, so now that we have these outputs, it's important to kind of figure out exactly what these numbers actually mean. So in the case of these outputs, what larger numbers mean is a feature was detected. So as we can see in the top left here, we have 80, and this is a much larger number than any of the other numbers on the output section. And because the 80 is in the top left, what that actually indicates is an edge feature was detected in the top left-hand corner of the image. And as you can see from the grayscale image, there is indeed a very distinct edge feature in the top left-hand corner of the image. 40 as well is also a moderately high number, not quite as high as 80, but still relatively high. And that suggests there's also an edge feature in the bottom left-hand corner of the image, just not quite as pronounced. And as you can see in the grayscale photo, there is actually somewhat of an edge feature just here. Not quite as pronounced as the one above it, but there is definitely one there, and that's been picked up by the convolutional filter. -10 and 5 are quite close to 0, so that suggests there's no real edge feature present in the image. And again, if we look at the image in the top right and the bottom right, there isn't really any edge features present. So I hope that gives kind of like a general idea as to how convolutional filters work and how they're able to detect particular features in images. So obviously, these numbers could be anything and could be detecting any type of feature. I've just picked an edge feature for this example. But it's a very, very general concept that can be applied to many different applications. Okay, so the data sets that we used for this study were a hyperspectral data set taken from the Pavia University in northern Italy. So in the bottom left here, we have a true color image of the data set. So that's basically just an RGB photo. You can see the university campus. And just to the right of that, we have the associated ground truth labels. So all of the colored areas are the labeled areas of the image, and all of the black areas are the unlabeled areas of the image. And so what we're going to do is train the models on the labeled areas and then get the model to classify the rest of the image. So you get the model to label up all of the unlabeled areas of this image here. The second data set that was used in this study was a simulated satellite data set. Now, what this actually was is a modified version of the hyperspectral data set. And what exactly was done to the hyperspectral data set was the spatial resolution was downsampled from 1.3 meters a pixel to 2 meters a pixel. The number of spectral bands was reduced from 103 spectral bands in the hyperspectral dataset to only 8 in the simulated satellite dataset. When I say spectral bands, I mean the number of wavelengths at which measurements were taken. And random error sources were also added into the satellite dataset to sort of simulate error sources that you would usually expect when gathering data from satellite sensors. Okay, so I'll briefly introduce the primary model used for this investigation. So it's called the Spectral Spatial Residual Network, also known as SSRN. And it consists of a spectral learning sequence, a spatial learning sequence, and then a final class prediction layer. So the spectral learning sequence basically uses convolutional filters along the spectrum of each land cover class type to detect certain spectral shapes and spectral features. And then the spatial learning sequence, what that does is say you want to classify a particular pixel of a hyperspectral image. The spatial learning sequence will actually look at some of the surrounding pixels and try and pick out sort of spatial features and spatial contexts associated with particular land cover types. So at the bottom here, I've got a very brief schematic of sort of the order in which the model learns these features. So we have the input data, which would be the hyperspectral image or the satellite data image. Spectral feature learning, so looking at the spectra of each land cover class type and learning the appropriate spectra. Spatial feature learning, so that's looking at the spatial context and the surrounding pixels to try and pick out spatial features associated with each land cover class type. And then we have the final model prediction. So the second model used in this investigation is the Spectral Residual Network, also known as SRN for short. This model is actually identical to the SSRN model, with the exception that it has no spatial learning sequence. So the reason for using this model is to assess the importance of spatial learning when classifying urban land cover types. You know, how important is spatial information, basically. Okay, so moving on to the actual classification results. So on the bottom left over here, we have the true color image again, the same as before, as well as the ground truth labels, again, the same photo as before. But now on the right here, we have the model predictions. So this is the SSRN model predictions on a hyperspectral dataset. So as you can see, all of the black areas of this ground truth picture have now been filled in with actual model predictions of what's there in the image. And as you can see, the model predictions also match very closely with the ground truth labels. So for example, originally we had meadow up here, and the models predicted meadows extending down this direction. And we can see this red here is tarmac, so that's all the roads around the campus. And the model has correctly predicted roads in the same parts of the campus. So you can see sort of by eye that the model has performed quite well and agrees quite strongly with the actual ground truth labels. So actually looking at the numerical results, the SSRN architecture achieved an overall accuracy score of 95.22% on the hyperspectral data and 89.63% on the simulated satellite data, whereas the SRN model achieved an overall accuracy score of 95.77% on the hyperspectral data and 87.99% on the simulated satellite data. So immediately what's obvious from these results is that the SSRN model and the SRN model perform very similarly on the hyperspectral dataset. We've got 95.22 versus 95.77%. What that suggests is that the spatial learning sequence actually is quite unimportant when you're working with hyperspectral data. The reason being is that there's enough spectral bands in the dataset, that there's enough spectral information that it's just not really required. However, when looking at the satellite data scores, we have 89.63% for the SSRN model and 87.99% for the SRN model. So here we have around about a 2 percentage point difference. This might not seem that significant, but this accuracy score is actually somewhat diluted because that's the accuracy score for the entire image. There are lots of areas in the image that are quite dirty. There's lots of different classes present, and we're not really that interested in those areas because both models perform equally poorly. Whereas when you look at sort of more homogeneous areas of the image, areas where there's only generally one class type present, the difference in accuracy is more like 5 or 6% between these two models. And that's really the areas of the image we actually care about. So there's about a 5 or 6% percentage point accuracy difference between the SSRN model and the SRN model on simulated satellite data. And what that suggests is because there's less spectral information available in the satellite data, with there only being 8 bands as opposed to 103, spatial context is very important for distinguishing between different land cover types. It sort of complements the spectral information, if you like, in classification predictions. Okay, so the general conclusions of the study are deep learning architectures are a viable option for successfully identifying urban land cover types. As we saw, we get sort of about 96% accuracy on hyperspectral data sets using deep learning and sort of around 89% accuracy on simulated satellite data sets. Spectral information is sufficient for land cover prediction with hyperspectral data sets, just simply because there's a lot of spectral information available to the model. So spatial information isn't really that important. Spatial features are particularly important though when looking at satellite imagery, and there's not much spectral information available to the model, only being 8 spectral bands as opposed to 103. So further research that could be done to further validate this approach include using larger data sets. So here, obviously, we've only used one image. Generally, neural networks contain a large number of free parameters or degrees of freedom, if you like. So it requires a large amount of data, basically, to train all those free parameters. So definitely tests on larger data sets would be required to further validate the results from this particular study. Additionally, data sets with a large number of vegetation types and species could also be investigated. Obviously, the goal of this research is to distinguish between, not only map out where vegetation is, but to distinguish between species and vegetation types. In this data set, we only had trees and meadows as our natural land cover types. So it could be better to sort of test the model on maybe distinguishing different species of tree or different types of meadow or different types of shrub and grass, just to sort of test the model's overall ability to get more specific about distinguishing different types of vegetation. Thank you very much for listening, and are there any questions?
Thank you very much. Fantastic presentation. There are some questions. I'll have to admit that you've actually answered a few of them as you've gone through your presentation. You're very thorough. I have actually a question from my end. As someone who's also done some work on artificial intelligence related classification, is what sort of level of accuracy would you see needing to be achieved before something like this could be used in like a practical professional setting?
Honestly, the accuracies we got from the study were probably sufficient. I mean, that's a very good question. It probably depends very much on the specific context of what you're trying to do. If you're just trying to map out the locations of urban vegetation and sort of analyze the sort of benefits, and sort of, I guess the real goal of this research in general is to identify urban areas in need of development, so which could do with more urban vegetation and greenery. So 95%, 90% accuracy is definitely sufficient for that. Obviously, with other applications, you might want more or less. Yeah, it really does depend on the context, but for this specific application, yeah, about 95% is good enough. Yeah.
Thank you. And actually, that feeds into another question we've just had, which is sort of what are some of the other applications of this model, perhaps if you have those high levels of accuracy?
Oh, great question. Really, there's a never-ending list of applications for neural networks. One obvious one is facial recognition, say in smartphones and stuff. So that's generally how facial recognition works. It's generally neural networks with convolutional filters identifying facial features. So that's one of the massive application of neural networks. Convolutional neural networks is also just a very small part of sort of the science as well. Standard neural networks can be used for all kinds of stuff. You can literally use it to say even predict house prices. For example, that's one good example. You might input some information about a particular house, like the square footage, how many windows and whatnot, and that can be used to predict the value of a house. So it can be used in that context too. Yeah, I mean, specifically convolutional neural networks are used in imagery. So satellite imagery is quite common, or facial recognition. And yeah, there's really very much an endless application of neural networks.
Thank you. Yeah, a brilliant answer. I would actually just say if anyone is on that note, what you talk about house pricing reminded me myself. If anyone is keen to learn a bit more about AI, it's a really useful course that you may have also done, Ben. Google have a free sort of 15-hour crash course introduction to AI, and goes through supervised and unsupervised machine learning bits of neural networks as well. So I just thought I'd bring that up. But yeah, thank you so much for answering those questions and for a fantastic presentation. Really appreciate it. It was an absolute pleasure having you on. And
yeah, thank you. Pleasure to be here. Thank you.
We will now have a short 15-minute break before we go into our final block with our last three speakers. Hello and welcome back to our final block of 3 speakers for the UKSEDS Student Space Symposium. We're about to go into our next talk by Shona Jane Ferguson, which is ground truthing land surface temperature datasets in an urban area. Shona is an applied meteorology and climatology postgraduate master's student at the University of Birmingham. She previously completed a BSc with honours in mathematics at the University of Glasgow. Her research interests are centred around satellite data and its uses for both meteorology and climate change. However, she also has a keen interest in chaos theory and wrote her undergraduate thesis on fractals and the Mandelbrot set. She has a strong passion for science communication and has volunteered for a science communication group for around 3 years now. Hi there, Shona. It's great to have you.
Hi.
You're welcome to start your presentation whenever you're ready.
Okay, I'll just start sharing now. Can you see that okay?
Yep, that's perfect.
Perfect. Okay, hi, I'm Shona Ferguson and I'm going to be presenting ground truthing of land surface temperature datasets in an urban area. This was my master's thesis and I was supervised by Professor Lee Chapman at the University of Birmingham. So this next section will introduce my aims and objectives. It will outline the main concepts behind my research and it will introduce why I chose my study area. So the aim of my research was to explore the relationship between land surface temperature and road surface temperature across the urban area of Birmingham over the winter of 2020 using a network of infrared road surface temperature sensors and modest LST data. So road surface temperature will be shortened to RST and land surface temperature will be shortened to LST during this presentation. To achieve my aim, I plotted the winter nighttime urban heat island map of Birmingham using road surface temperature data and land surface temperature data to map the thermal climatology and compared the two. I also carried out a regression analysis of LST and RST for each sensor site to assess the relationship. So you might be thinking why road surface temperature is important. As we all know, the UK does not have the best weather, and in winter there can be snow, ice, and frost, which can cause very dangerous driving conditions. Winter road maintenance decisions can assist in the prevention of traffic incidents in winter, but the UK spends over £140 million annually on winter road maintenance, and a further £100 million is spent repairing salt corrosion damage to vehicles and structures. Therefore, road surface forecasts are very important for providing safer roads and minimising road maintenance costs. These forecasts are very dependent on road surface temperature, and road surface temperature is usually interpolated between sites using thermal mapping, which can cause quite a large degree of error. So the idea behind this research is that LST could be used to increase the spatial resolution and therefore reduce the error involved. In terms of applications of land surface temperature, so satellite data is being continuously used more and more in meteorology as it provides increased spatial coverage and a consistent, repeatable and low-cost methodology for the end user. NASA's MODIS sensor is a vital tool in measuring LST and is found on both the Aqua and Terra spacecraft. Many previous studies have explored the relationship between air temperature and land surface temperature with the view of LST being able to predict air temperature, but there's very limited existing research into the relationship between LST and RST. And it is thought that this relationship would be a lot more accurate because air temperature is usually measured 2 meters above the surface, whereas road surface temperature is obviously measuring the surface. temperature. Partly the way that we'll address this research gap is by comparing the urban heat island maps using land surface temperature and road surface temperature. The urban heat island is an urban area with a higher temperature than the surrounding rural areas. It's largely caused by increasing urbanization and can have very negative impacts on health. There's a vast amount of research using land surface temperature for the quantification and mapping of the UHI. And most studies focus on the summer UHI, as this is more likely to have more negative impacts on health. There was no existing research found using road surface temperature to map or quantify the UHI effect. And the study area chosen was Birmingham, which is the second largest city in the UK. As you can see in this map here, I've popped in some notable locations and the road surface temperature sensor locations as well. Birmingham's representative of many other cities across the world, and it was chosen due to its distinct range of land use present and the recent implementation of road surface temperature sensors across the city. So this next section will detail the data chosen and the methodology followed. My road surface temperature data was taken from the Birmingham Urban Observatory. The data is taken from WinterSense infrared thermopile sensors that take 30-minute averages at 24 sites across Birmingham. They take measurements with a 1-degree accuracy and are mounted about 3 to 5 meters high on lighting columns 2 meters from the road, as seen in this image. They're tested in sophisticated climate change chambers, and any extraneous data is flagged by their software. The land surface temperature data used was obtained from the MODIS sensor on NASA's Aqua satellite. It takes infrared images with a 1 kilometer squared spatial resolution. The Aqua satellite was chosen over the Terra satellite because LST accuracy is improved late at night, and the Aqua satellite takes its images at 1:30 in the morning, whereas the Terra satellite takes its images at 10:30 at night. In terms of data processing, the study days that were chosen for low cloud cover so that the satellite images had a full coverage of Birmingham. In order to do this, the standard deviations of the road surface temperature data were calculated as a proxy for atmospheric stability. The days with the highest atmospheric stability were the satellite images were previewed to choose study days with clear skies over Birmingham, and then these images were processed using ArcMap to extract the LST data. And the methodology followed. The nighttime UHI map was plotted in ArcMap using both the LST and RST data for all 10 study days. The UHI intensities were then calculated by taking the rural temperature away from the urban temperature. Scatter plots were made for comparison of the LST and RST UHI intensities, and scatter plots of LST versus RST at each sensor site were also formed. A linear regression analysis was performed using land surface temperature as the predictor and road surface temperature as the outcome, and then spatial plots of the slopes, intercepts, and R-squared values from the 24 regression equations were examined for any spatial trends. And this last section here will be the results, the discussion, and the conclusion. So these are the UHI maps that were produced from my research. They're shown here in decreasing order of atmospheric stability. And they're labeled with the dates and their atmospheric stabilities. So as you can see here, for the land surface temperature maps, there's a high degree of temperature variation, and all of the maps, or most of the maps, show a fairly good UHI effect, with warm areas over the city centre and colder areas over more rural places with urban parks. The maps with less temperature variation are generally found when there is more atmospheric instability. In comparison, for the road surface temperature maps, only 3 of the maps really showed comparative UHI effects to the land surface temperature maps, and these were taken at the end of February, which tends to suggest that road surface temperature might be better at plotting the UHI effect in spring and summer than in winter. The 5 maps with the lowest atmospheric stability don't show much temperature variation at all, where we can't really see much of the spatial trends. So we would like to repeat this, ideally in a time where there's going to be more atmospheric stability, such as summer. And this is the scatter plot of the UHI intensities, land surface temperature against road surface temperature. There's a weak positive correlation of 0.43. This implies that LST and RST don't strongly agree when quantifying the nighttime winter UHI in Birmingham. This would also imply that RST is not as reliable as LST at mapping the UHI, as LST is generally found to be reliable when plotting the UHI. And for a direct comparison of RST and LST, this is just an example of one of the scatter plots I made showing the land surface temperature and road surface temperature readings at each site over one day. As you can see, there's significant variation, and there was significant variation across all the days, with neither LST nor RST being consistently higher than the other. But in over 68% of cases, the measured difference between LST and RST was within the combined error of the datasets, which is positive. These plots show the number of cases where LST was higher than RST and the number of cases where RST was higher than LST. As we can see, the time of year plays a large role, and this is thought to be due to an increase in solar altitude in January and February, which means more concentrated solar radiation on Earth's surface. This would make RST increase more than LST, as the road surfaces absorb all wavelengths of light due to the tarmac roads with black surfaces, and they convert this energy to heat. Whereas for land surface temperature, there is a variety of surface types which might not absorb as much light and therefore not get quite as hot. And for the linear regression analyses, correlations were found to be between 0.633 and 0.964, which are quite strong positive correlations. The average temperature difference, as you can see in figure A here, shows low site-specific variability. So the spatial trends don't really show very much, as there wasn't very much variability between the sites. For image B here, you can see the R² values for each site. There was 40.1 to 93% of the explained variability in RST was accounted for by LST, but most of the readings were above 60%. And for the slope values, 87.5% of them were above 0.7 degrees centigrade, and these represent the unit change in RST if LST was increased by 1 degree. And for the intercepts, they show the estimated RST if the measured LST was 0 degrees, and 83.33% of these were close to 0 degrees. This is important as it shows that LST is relatively accurate in predicting RST for temperatures around freezing, which would be very important for salt distribution. The greatest inaccuracies in the relationship were generally found in the southwest of Birmingham, as you can see in these graphs. This is thought to be because there is a large urban park in this area, so the LST is measured across 1 kilometre square pixels, including the urban park, but the RST is measured in point locations on the roads and doesn't account for the rural surroundings. So in terms of future research, people could investigate whether the road surface temperature would be better for mapping the summer nighttime surface UHI rather than the winter one. A larger network of road surface temperature sensors could minimize the interpolation error in the graphs. The Pascal Gifford stability classes could be used to categorize the study days rather than using standard deviation, but this would really be done with a larger data set. If the study was conducted in summer, there would be higher atmospheric stability and a more intense UHI effect. And other factors could be included in the regression analysis, such as land use, altitude, and traffic levels and road types. To conclude, the UHI effect is clear across a range of stability classes when mapped using land surface temperature. Road surface temperature does not show sufficient temperature variation on atmospherically unstable days to show the UHI effect, but a strong relationship was found between RST and LST at night at the neighbourhood scale. We can deduce that land surface temperature could be used as a proxy for road surface temperature, provided the limitations of the study are accepted. This could cause huge implications for the ability to predict where and when salt spreading is required. And here are some of my acknowledgements and my references there.
Okay, thank you so much. Brilliant presentation. We have time for one question before we move to our next speaker. And so the question is this method not offset by localized temperature increases caused by running car engines in peak traffic hours?
Yeah, so that's why I suggested for future research possibly taking into consideration traffic levels and things, because it could have like an adverse effect. So future research is required to understand the relationship a bit more in depth. Yeah.
Brilliant. Thank you. Thank you so much for coming on and for giving your presentation.
Thanks very much.
We will now be moving to our next speaker.
Thank you.
So we will go over to Mart for his. Hi there, and welcome back for our next talk. We've got Aaron Arelevo presenting on numerical simulation of ion drives for space exploration. Mart is a 23-year-old recent Master of Aerospace Engineering graduate from the University of the West of England who likes anything space-related. Hi, Mart. It's great to have you here.
Hi. Do I just join now?
Yep, we're ready for you to present whenever you're ready.
Oh, all right. Oh, there must be two things. Okay, sorry, my bad. Sorry, mistake on my part. Okay, let me just present my window. Okay. Hopefully everyone can see that. I'll full screen it as well.
Yep, we got it. Brilliant. Take it away when you're ready.
All right. You full screen this. All right. Hi, everyone. My name is Aaron Arelevo, as these guys already said. And my thesis title is Numerical Simulation of Ion Drives for Space Exploration. A bit about myself. I'm a recent graduate from UE with a Master's of Aerospace Engineering. I have industrial sort of experience in mechanical design from my industrial placement as a junior design engineer. And most recently, I have become a sort of certified data analyst from Google's online professional data analytics certificate. Like I said before, I have background in mechanical design, 3D modeling, and software development. And right now, I'm currently taking machine learning and data science courses online, and also in the hopes of applying to become an incorporated engineer near the IET. So let's start off with a quick introduction about ion thrusters, I guess. Ion thrusters are essentially alternative electric propulsion alternatives for spacecrafts rather than chemical propulsion. This is making it so it's like non-carbon such harmful emissions being exhausted. And along with that, ion thrusters are very, I guess, fuel efficient in a way that it can be used for longer missions rather than chemical propulsion in itself. And with that being said, it's used on most modern satellites, such as below. You can see below the pictures on the left is the NASA's Dawn spacecraft, which is used for asteroid sampling for deep space missions. And on the right, you can see it's SpaceX's Starlink mission. Satellites. However, it is still too weak for two orbit situations due to atmospheric conditions being too much of an impedance. And of course, the exhaust being ions, it's still, I guess, weaker than chemicals. Therefore, we still use chemical rockets. Then you can picture on the left is, of course, SpaceX's Starship. And then on the right is the rocket to get the Starlink satellites into space. With that being said, rocket technology is evolving more rapidly than ever, starting from the 1960s all the way up to the 2000s. With that being said, there has been large amounts of data and present data from this. This cannot be said, however, for ion thrusters due to the fact that the testing and environmental conditions that you need to do is very expensive, resulting in very few test sites and viable setups in the world. So to advance our rocket technology, and in this case, ion thrust technology, we need to turn to numerical data rather than experimental. More specifically, we will turn to numerical simulations. If you think about CFD and FEA sort of analysis, you think like ANSYS and SimScale. This is sort of similar to that, where it was able to produce results akin to experimental testing, and it's almost available to almost anyone, and with it being extremely cost effective. So this is where my thesis comes in. With all this being said, my thesis is to produce a numerical simulation of an ion thruster that can be used for spacecraft design suited for deep space travel, such as the NASA's Dawn spacecraft. More specifically, I needed to deliver a solution of a version of the solution rather than the whole simulation. This is due to time constraints with a sort of master's thesis length of 7 months. With that as well, I need to also simulate specific conditions of it. So what I chose to simulate discharge chamber simulations just to get the plasma phenomenon and ionization correct, mostly due to the fact that these are the main properties of thrusters and I guess the exhaust as well. From that, I needed outputs from the simulation. So I chose thrust, exhaust velocity, and specific impulse, mostly due to the fact that these are the three measuring parameters used for comparing spacecraft and thrusters itself. I coded this on Python, mostly because the NumPy libraries are very effective. Along with that, I could have libraries with it to sort of develop it into a better software. Like I said before, NASA's Dawn spacecraft was sort of talked about a lot due to its mission. Therefore, it will be used as my baseline model for this simulation. And with that, I needed a validation sort of success criteria. And what was chosen was a plus minus 24% from the baseline model. So essentially, if the simulation produces a thrust value that's within 25% from the baseline model, it's deemed successful to like produce thrust values correctly. And on top of that, finally, to finish it off, I needed a sort of environment for this simulation. So I chose a 2D electrostatic model for the same reasons as before, where I needed to deliver it in a 7-month academic year. So that being said, I need to talk about the methods and models I will be using. The main problems with simulations, especially something like this, is mostly due to the fact that it's very computationally heavy with the scale of almost 10 million particles, where you have to sort of calculate particle motion, electric fields, collisions for each particle. From literature and research, we have found that most papers doing the same topic, most, if not all, have used the same model, which is the particle ensemble method with the variation of the direct Monte Carlo method, or in short, the PIC-MCC model. This is mostly due to the fact that it can simulate motion of charged particles, and with the sort of MCC model being added on top of it, it could calculate the collisions of neutral-neutral, electron-neutral, ion-neutral, and whatever you needed to code. On the right here is the sort of main equation that we need to solve for the electric field, which would be then used to sort of input into velocity, the particle, particle position, and from that, the force of it. This is just saying that we need to use the particle ensemble method along with it. Additionally, on top, we needed to group the particle groups into macroparticles. So if you can think of 10 million particles, we need to sort of scale that down to 10,000. This is what we're going to do with that. Additionally, we will assume electrons are a fluid rather than individual entities. This is so that we don't have to sort of simulate another group of I guess, particles. So we're going to simulate neutrals and ions, and the way that we are going to simulate the motion, the properties of it, and as such. So you can see here on the left, this is a typical PIC code scheme, where it's like a cyclical kind of scheme going round and round via various iterations going into each other, with inputs from each iteration going into the iteration. So inputs. So the outputs of each iteration is going into the inputs of the next iteration. If that makes sense. Then, of course, here these are the core equations that we need to solve from this. These will be expanded upon later. However, I want to briefly touch about the boundaries. When we think about boundaries in a simulation, especially in this one, we want to have it so that it's like reflecting trajectories of the particles. So if you think of a tennis ball bouncing off a wall, that's what we need to sort of replicate in this way. Depending on the boundaries, you need a screen grid. So if you think of a screen grid as at the very end, where it's closest to the actual exhaust of the discharge chamber, this will take in the ions, as in it will just absorb the ions and just shoot it all the way out. And from that, we will take the force and velocity offset ions that are being shooting out as well. So when we put into context and expand upon these equations, you can see on the right, we have the sort of Maxwell's equations of electric field, which is a function of potential, and in this case, it's distance. And you can see here, we use Gauss-Seidel method just to expand upon it, just to make it a sort of iterable solution. And then from the particle advancing on movement, we will use the Suva equations, essentially, just to make sure it's just very simple and, I guess, computational. And you can see on the left-hand side is just a diagram of like where all these equations would be using. And in the red, it'll be used like pretty much everywhere. And then if we look closely into what's happening in the collision of it, we have the particle collision, which was handled, like I said before, by the direct Monte Carlo method. You see here, if this statement is true, with R being a sort of random number for each iteration and each particle, if the statement is true, then the sort of collision will take place and ionization will happen, causing a positive ion to bounce out, and then neutral to not exist, and yeah, all the sorts of ionization type of stuff. And then from this, we could have a particle force velocity with a force being sort of expressed by the Poisson's ratio, with an elementary charge being Q, and E being, of course, electric field. And then below is, of course, the subsequent velocities of said particles. And then, of course, we have the outputs of the thruster. So we have the velocity of the actual thruster itself using the conservation of momentum. And then we have thrust here, which is said more in my paper. However, I'll briefly describe on it. It's essentially just a function of the ion beam current, which is JB, and of course the outputs of said thruster or said particles. With that all being said, we have now to discuss results. So what I've done is I have produced a 700 time step solution with the contour plots from left to right. The left being a particle distribution within the chamber, and the right contour plots being the particle velocity and potential. If we start for the left, we can see that the blue markers are neutrals and the orange markers are the ions. And if we sort of analyze it in a way, we can see that sort of follows the same like erratic behavior that we would sort of expect in a like collision on a gas heavy sort of environment, where it's just erratic behavior bouncing off walls and stuff. This same goes for the right hand side with particle velocity, where it just has the same sort of contour plots of erratic behavior. However, the potential on the right is a bit more static. It's possible fault due to the input discharge voltage being sort of overwhelming to the sort of potential solver that we were trying to solve. So you can see that at the very end it's almost up to 27, 28, which is near enough the discharge input voltage. So the potential that was calculated is almost negligible compared to it. So with that being said, we have on the left the sort of auxiliary, I guess, results used for just further evaluation, which is okay. But on the right is what we actually need to sort of compare. These are the three parameters that we will use to compare to the baseline model. And then we compare it to the baseline model with PD being percentage difference. We can see that only the exhaust force, being 17.76% difference, is only within the success tolerance, with exhaust velocity and the specific impulse being almost 100% out of range. So when we talk about evaluation of the project, I want to talk about limitations as it is. So we could only handle large cases, mostly because small geometry would cause zero values to appear in the weighting scheme, which would encoding would result in a floating point error where you can't divide by zero or times by zero. Different collision index. So if you remember before in this previous slides, the value R was a random value between 0 and 1. However, we needed to change it from 0 to 0.1. This is mostly due to the fact that we needed to have it run relatively fast to fit within the 7-month project scope. Additionally, like I said before, about the sort of zero values and floating points, we needed to have a non-zero reference potential. This is so that it wouldn't, of course, be divided or times by 0. So when we talk about the results with why there's such a high percentage difference, we could talk about the possible faults within it. One possible fault would be due to a magnetic lack of magnetic field. So from Maxwell's equations, ion velocity is dependent on magnetic field. You can see the equation below there with B being the magnetic field, E being the electric field, of course V being the velocity of the particle. As you can see, it's quite dependent on it, and with this being the subsequent velocity. So that might be due to why the results have been so out of place. Additionally, the solution was way too fast to run. When I looked at it a bit more, a 700 time step solution was roughly about 0.07 seconds in real time. And when we look at the NASA's Dawn spacecraft, it took almost 4 days to reach a 60 miles per hour velocity. So in conclusion, the guess results kind of showed that the code was very primitive in a way that it did show promise in our future development. However, it still needs a lot of calibration in a way. The success was found within computing accurate boundary interactions with potential and electric field solving, and of course, particle movement, like I said before, with the erratic behavior with it. However, it did fail, like I said, with calibration of results to be correct within the success tolerance of plus or minus 25% from the baseline model. And then, of course, limitations of it having non-zero values and as such. Future work would be, of course, to expand on it. And but first, we need to debug the code. I would first probably debug the collision index to allow for a original index range from 0 to 1 rather than 0 to 0.1. This is mostly the fact that this will have potentially correct values at the end. But the one that I really need to put my head down and really get into is the electromagnetic environment. So when we talked about possible faults before, we need to sort of get magnets in there really, and just get that B value just to get it there. And like I said, it could potentially fix the results and errors. So I guess these two sort of future works would also expand upon it. However, this is more of a debugging kind of problem. And I think that's all there is to it. I guess thank you for listening.
Thank you. Again, another brilliant talk. We probably have time for just one question.
Oh, okay, that's right.
If an ion launch vehicle were ever hypothetically created, the Newtonian laws show that you would need a large mass of propellant.
Yeah.
As it's relatively inert, it's difficult to produce on a large scale. So how do you think, such large quantities could maybe be gathered without producing a very large price tag?
I would say I don't think it's very necessary. If you're talking about something like that, you probably need like a really innovative like gas. Really, I think you want like really good propellant for that, rather than a really big like gas chamber just to shoot out as much propellant as you want. So you really need like something that's heavy, while it's I guess ionizable in a way that like ion thrusters have been in the past. So we probably need like a more denser, I guess, propellant with the same ionizable properties, along with the same like exhaust as we need. So as long as we could find that or just try to work on that, then yeah, we would probably have like a really good ion thruster like environment now. But as it stands, I don't think we could have that right now.
Brilliant, thank you. That's a fantastic answer. And again, thank you so much for coming and presenting. It was an absolute pleasure to have you.
Thank you.
Again, as we've been doing all day, we'll take a very brief break before we go into our last talk of the day. Hello and welcome back for our final talk of the day. Last but not least, we have Elias Abala presenting design and validation of a low-cost and reusable resonant igniter using modern additive manufacturing methods for use in rocket propulsion. Elias is a fourth-year mechanical engineering, MEng aeronautical engineering student at the University of Glasgow. Having previously developed a nitrous oxide catalytic igniter as part of his Carnegie Summer Scholarship Program, Elias has developed a great interest in space and launch vehicle propulsion systems and hence aims to become a propulsion engineer when he graduates. He is currently developing his own augmented spark igniter and larger water-cooled 50-Newton engine intended to be tested nearing the end of the year, and is also a member of GU Rocketry's propulsion team developing the feed system for the 500-Newton Chimera 1 hybrid engine. He attends the fortnightly Astro Agency Space Bar discussion panel to meet and engage with other similar space interests. His current academic interests are the development of a lightweight, high-flow piston pump and resonant igniter for rocket propulsion systems. Hi, Elias. It's great to have you here. Thank you very much for coming along.
Thank you so much.
As has been the case, we're ready when you are. So feel free to share your screen and get to it.
Let me just share the screen now. There we are. I should be sharing my screen. No.
Yep, we can see that. So take it away when you're ready.
All right, perfect. So as I was introduced, my name is Eli Sobla. I'm a fourth-year aeronautical engineering student at the University of Glasgow, and I'll be discussing how I developed a resonant igniter over the summer using a modern additive manufacturing techniques with the aim to minimize the cost and maximize the reusability of the igniter. Let me see if I can move the page. There we are. So firstly, I'd like to give an introduction generally on rocket igniters. Rocket igniters can be generally classified as anything that's used to start the main engines of a given rocket propulsion system. They can vary from pyrotechnic ignition systems, which are used typically in model rocketry or solid boosters, to anything up to an augmented spark igniter or a plasma-assisted ignition system. So just examples for augmented spark igniter, you've got figure 1, which was developed previously, and figure 2, which was my personal additive manufacturing project you can see there. Overall, rocket igniters are extremely critical for a mission operation, and thus reliability is extremely important. What we've seen recently in the aerospace industry is a move towards old technologies which weren't available at the time. One of the technology which is extremely investigated at the moment is the resonant igniter. As you can see, Orbex's igniter is, if you investigate it closely, it's not explicitly said on their website, is a resonant igniter. So just give an idea on resonant ignition. Resonant ignition operates using a Hartmann-Sprenger tube, which more or less is a characterized tube with specific dimensions designed in such a way that a choked gas flow is entered into the tube to induce vibrations, and it's positioned in such a way from the exit of the tube, from the exit of the gas flow, so that Mach disk vibrations occur. And these Mach disk vibration instabilities lead to high amounts of vibrations and then heating to the gas. So if you have an oxidizer and fuel injected into that, you can then induce a dieseling reaction and thus combustion. Just to briefly discuss an additive manufacturing methods, if you're not too familiar with additive manufacturing operates through material deposition, typically done through layers, as you can see through the binder jetting example I've got in figure 6 and the selective laser melting process I've got in figure 7. These are extremely efficient, as the excess material that's not used in the printing process could immediately be returned back into the production line to create new components, which is good, as opposed to reductive manufacturing, where the chips that are produced need to be remelted back into stock. And again, as I said, there's quite a few new technologies being used. My technology I've used in my project was binder jetting, because it's extremely cheap, because it only operates using an adhesive printed through almost like an inkjet printer, to deposit the adhesive in specific locations, which is post-entered into an oven. So the objectives of the overall study was to design the resonant igniter to operate on long run times and long frequencies. So in this case, I've set a minimum cumulative runtime as 120 seconds, which is extremely high as opposed to traditional igniters, just to emphasize the amount of reusability that I want the igniter to be able to do. Propellant selection I chose was based on what was available at the university. So at the university, I wasn't able to access any type of complex igniters, propellants, or such as nitrous oxide and stuff due to legislation. So I chose isopropyl alcohol and gaseous oxygen, and a low chamber pressure being 5 bar was my selected pressure. Material properties were derived from the stainless steel bronze mixture, which is extremely high thermally conductive. That's used in binder jetting. It's extremely common material used. And all the properties you can see in the design specification were derived from there. Any wall thicknesses and wall lengths were derived from a previous study we did into print resolutions for binder jetting prints. So before we started, we did a literature review on resonant ignition. So there was two projects we investigated. There was the NASA Acoustic Development Program and the Firefly Group's development program into resonant ignition. The NASA's acoustic program operated in the early 2000s, late 1990s. These operated using the Hartmann-Sprenger tube being contained within the chamber, which was space efficient, however, is clearly inefficient. You could see in figure 10 and figure 11, these were good. Again, as I said, it was space efficient. However, there was no direct method of cooling of the resonant chamber, the Hartmann-Sprenger tube, thus leading to short cumulative runtimes and thus making them expendable, which isn't ideal. We proposed to take the method the Firefly Group did, which was regenerative cooling on their igniter. As you can see in figure 8, they're quite bulky, different shape, different modularity compared to the NASA resonant igniter.
but these had longer cumulative times, however, still struggled, even though using regenerative cooling as a method of minimizing heat temperatures, suffered from material ablation, which means that the materials were starting to break down over long periods of time, causing, again, material failures. So the method of analysis we did is to work off from the Firefly group's regenerative cooling. We designed a regenerative cooled system using a few methods we developed. First of all, we had to derive combustion properties. We did this through NASA's CEA program, otherwise known as Chemical Equilibrium Applications with GUI. We used the GUI version of that. We did an analysis on different oxidizer to fuel ratios to calculate combustion temperatures and combustion pressures at given conditions. We also used the numerical methods based on S. Heisler and his textbook to calculate the regenerative cooling properties. So how we did this, we split up our combustion chamber into different sections, as you see in figure 12, just little sections split up in delta X distance. We then calculated the hot side heat flux for given conditions, the cold side heat flux, and then iterated them until those were equal, i.e. we had steady state. From this, we would then derive the hot side and cold side temperatures, which were then computed into an array file in Python. We built off from that program onto what we called the RCAS program, or the Active Regenerative Cooling Analysis program. This was also built in Python and coded in Python, and we optimized for those previous data using the channel dimensions and thicknesses. We varied them appropriately until we got minimum conditions in the cold side. Now, to prevent the optimization program from breaking any requirements we previously set in this table, we applied penalty functions. These penalty functions were for things like maximum temperature and maximum stresses, which we used basic equations for to derive the maximum stress using our factor of safety, along with some finite element methods to derive the stresses from there and the stress relations. And that would allow us to derive a perfect result in terms of the regenerative cooling dimensions and how they varied across the whole combustion chamber. From our research findings, as you can see, we'll start with figure 16. We found that lower OFs lead to lower stagnation temperatures, which was ideal from us. But when we did further investigation into the combustion plume compositions at the lower OFs, we found significant sections of graphite being generated, which was extremely problematic. As this, of course, was a sign of incomplete combustion, this harmed the ignitability of the mixture. We found in previous papers that indications of graphite affects ignitability, which would then be problematic, especially with resin ignition, as it could lead to depositions of like graphite or carbon inside our Hartmann-Sprenger tube, which was problematic. We used our previous study we did on OFs on ASI we built, the Augmented Spark Igniter, and we found an OF of 1 to be ideal. So we went forward with that. We took that data and then used RCAS optimization program to generate the graph you could see in figure 15, which was somewhat decent, you could see. Obviously, there was quite excesses in temperature near the throat, and the expansion section was extremely problematic, with temperatures exceeding 1000 Kelvin, which is bad. But that was preliminarily from our study of different parameters. We found it was limited by the coolant flow, which was the fuel, and the dimensions applied on the minimum dimensions we applied on our requirements and the resolutions of the print, which was problematic. Another thing to be noting is due to the coolant side temperatures being so significantly high, we had a phenomenon called nucleate boiling occurring, which was extremely problematic for the reliability of the simulation. Nucleate boiling can be only described as when a fluid comes in contact with a plate or a surface which is at a higher temperature than its boiling point, bubbles will form, be ejected into the fluid, and remove heat, which is extremely good from the point of regenerative cooling design, because it creates a buffer for you to, ensure that your temperatures don't significantly increase, and for the accuracy of your simulations to still be valid in real life. However, our design point was beyond the critical heat flux coefficient and beyond the nucleate boiling regime, and into the film boiling regime, where the bubbles were forming too fast and were generating a long gas layer, which effectively reduced the heat flux coefficient and then would increase the temperature significantly higher than our simulation would predict. So that reinforced that we really required another form of cooling, which would significantly reduce the heat flux more than we would expected in our simulations. We considered a few other options. One was chemical additives, including TAA, or silicon oil. We considered both of them. However, we wanted to ensure the flexibility of the overall system was valid and ensure that our system would still be able to operate in a commercial environment where these additives weren't able to be added just specifically for the igniter to operate. So we proposed film cooling, which is the injection of fuel, or in our case, the coolant, or a coolant, which is the fuel, along the combustion chamber to create a lining or protective layer which protects the walls of the combustion chamber from the high combustion temperatures in the center and reduces thus the heat flux. We used an analysis program to derive the film cooling percentages as a factor of the film cooling length, and we derived that the film cooling wasn't that efficient to be able to cover the entire igniter, which was problematic. However, we suggested that given that the combustion throat, it was the chamber's throat, and the expansion section was the only problematic areas, we would only cover those areas. And as such, we positioned our film cooling holes to be there. And once we decided the geometrical parameters from our requirements for our holes, we put it into optimization program, and we came out with 40% as being the ideal film cooling percentage to cover those dimensions, which, although is extremely high and isn't exactly the most efficient, because given film cooling, you're dumping extra fuel, which isn't that efficient, they allowed the igniter to operate under our conditions we desired for. So we accepted it. So in conclusions, you can see our developed igniter here and the geometry along with the coolant channel geometries along the throat. I've got a cross section there for you, just for vision. We successfully managed to design the igniter, theoretically. However, due to using a lot of semi-empirical relations, and especially the worries in terms of nuclear boiling and the heat flux coefficient not necessarily being accurate to what we expected, because we're not necessarily certain if the semi-empirical relation applies to the nuclear boiling regime, because it's not specified in the previous studies, we actually need to do physical testing. So as part of our further work, we're currently in the works of developing a test stand, and we've already ordered our igniter to be shipped to us. Hopefully, when it's manufactured, we'll have it within the coming weeks. And hopefully we can get a test stand running and and operate our test campaign to see if our igniter will function under coolant conditions using water. It'll be open loop. And hopefully, if that works, we can close the loop and use isopropyl alcohol as we designed for. Yeah. So here are my references. I'd like to make acknowledgements to my supervisor, Dr. Daniel Barbera, and the team MoFem for helping me with some of the finite element methods I applied in the project, and Mario Hernandez Mendez for helping with the digital twin technology I used in my ARCAS simulation. Thank you very much. Any questions at all?
Thank you. A brilliant presentation. We have a couple of questions.
So we designed the igniter currently working with 100% gaseous oxygen, which is we can probably approximate extremely well. For the isopropyl alcohol we're using, we tested it for the standard one we can get, which was 98%. In theory, we haven't done any physical testing yet, unfortunately, because of coronavirus limitations, but it should work. If we applied, one thing I mentioned about the additives, I said you could add TA or silicon oil to reduce the heat flux. Yes, if you added water with a different grade of isopropyl alcohol, say it was 92% isopropyl alcohol, you could reduce the heat flux. However, you sacrifice the propellant efficiency overall and the actual rocket propulsion efficiency, which is not exactly ideal if this was in an actual commercial setting where efficiency matters a lot.
Great, thank you. Our second and final question is, some of this research seems to be partially in the remit of a chemical engineer. What, if any, extra learning did you need to do to make the research possible?
So I had to do a lot of learning in terms of combustion equilibrium and learning how to do the NASA CA program. A lot of the regenerative cooling was based on thermal analysis, basic engineering stuff. I think that's you can learn online. I had to learn that myself. But in terms of the chemical engineering, I had to learn a lot about the combustion properties and combustion analysis. You can probably find a lot of the stuff in terms of how NASA CA works through a process called Gibbs-free energy minimization. Gibbs-free energy minimization, if you're ever interested in learning about how to analyze the combustion processes. And you could also use the NASA CA or RPA program if that assists you. But that's what I used as my learning programs and processes and methods to solve the combustion problems for the igniter.
Sorry, I realised I was just muted. Almost went the whole day without doing that. But you know, in traditional remote event fashion, we had to do it at least once. I said thank you very much for answering those questions. That was our last one, and thank you very much for your fantastic presentation and for your fantastic paper. So that was the final talk of the day. So now I'll give some brief closing remarks to sign us off. Thank you very much for attending the symposium, or all of our wonderful attendees, for making this event possible and for checking out the careers stand. I'd like to again thank our sponsors, Astro Agency and Bryce Tech, for making this possible, and for the British Interplanetary Society for making it possible for us to give some of these authors the chance to have their research published in a peer-reviewed journal. That's in fact the next stage of the symposium. The papers from all the people you heard from today will be reviewed, and the shortlisted ones will be submitted to the journal and then peer-reviewed before potentially being included in a special UKSEDS edition of JBIS. I'd also like to say a big thank you to the other UKSEDS volunteers who are not as outward-facing the event for me, Ria, Zaria, and Ollie, who have been helping with the tech side of things, as well as publicity and social media, as well as the rest of the organizational team who aren't here on the day, but have been working really hard in the past few months to make sure that this event could take place and work as hard as possible. I'd like to thank our captionists, 121 Captions, for doing today's captions. Part of our initiative is to make these events as accessible as possible, and we couldn't do such a thing without them as well. Just a couple more things. As I mentioned earlier, the recording of this event will be available on the UKSEDS YouTube channel shortly after we finish the event. So if there's any talks you missed or anything you want to watch over again, feel free to go and check it out. As I mentioned, we have a bunch of other interesting UKSEDS events coming up this month and in the coming months. And if you're interested in joining us or joining us as a volunteer, make sure you check out our website for details on how to do that. If you're interested in submitting an abstract for next year's Student Space Symposium, we tend to advertise the call for abstracts mid-summer, usually around early June. So make sure to note that down and keep an eye out for when we do that next time. Thank you very much again for attending, and I hope you enjoyed the event. Have a nice rest of your